If it has a heart, I don't see why not.
Sounds like some people do. You say emails every day? He's like the organizer.
Oh, no,
You say like,
I didn't read that.
I'm sure some people from. I just figured it was like. Yeah. Yeah, I guess we use I never remember what we can't just put to a process.
Well,
That's all you got. Fish, really? That one was a fish.
What's that?
The one in the photo was a fish. I was the only one that wasn't a picture. Yeah, that's
Out of it, I guess.
I worked it.
Oh, you do? Oh, okay. Concerning that these mics are always on. So if that happens and you're too close, that is dangerous. Oh, thank Yeah, that was.
That's how it's
On the other side? Oh, yeah. Okay. Welcome everyone to the third day of the BPF/networking track. Today we have more of networking kind of talks, and we start with David about IRQ and zero copy.
Hello? I'll pick it up. Okay. Hello? Yeah, good morning, everyone. My name's David, and I'm a software engineer at Meta. Today, I'll be talking to you about adding zero copy to the Linux kernel using IRQ as the user API. And this is the work that I'm doing in collaboration with my colleague, Pavel, who's in the audience somewhere. Yeah, cool. So agenda for today, I'll first start off with the kind of give some context of the problem, why it's important, why we want to solve it, and then I'll move on to a very quick overview of IRQ for those of you who are not familiar with how it works. Then I'll talk about the kind of design and implementation for our proposal. We'll look at some early results that we've been getting. And then we'll talk about the kind of current status of the project and what we want to do next. And then I'll leave a little bit of time at the end for a short Q&A. Okay, so why do we want to have zero copy in the RX path? So the Linux kernel networking stack adds a bunch of overheads to on the receive path. In order to receive each packet, it has to make several paths through both PCIe and also to the system DRAM. So the packet first gets DMA'd into kernel memory in the host. So that's one trip over PCIe and one trip over the memory bandwidth. And then in order for the user to actually receive the payload for the packet, there needs to be another copy into user space, which adds another copy. It adds another trip over the memory bandwidth as well. So this, in certain situations, can fully saturate the memory bandwidth, and we kind of see that in production. And copying as well has a CPU overhead, and as the line rate increases, that overhead kind of adds more and more as well. So how do we solve the problem? But this has been a problem for a long time, and we've known that in the community. The kind of classic way of solving this is, well, let's just get the kernel out the way. Let's bypass the kernel entirely. And there's a whole host of different technologies to do this. I've listed some of them in the slides here. We've got DPDK, we've got PF ring, we have AF-XDP sockets, and also we have Rocky or RDMA as well. These definitely work. They can give you high throughput, low latency, some mixture of both. But the kind of problem with these solutions is, since you're bypassing the kernel, you need to handle the kind of networking stack in user space, right? Something has to do the work, whether it's the kernel or user. And in addition to that, all of your libraries and services that kind of expect the presence of a networking stack, they're not going to work anymore out of the box. So you kind of have to redesign and re-architect your entire system around these solutions. And that is very expensive in terms of how much work needs to be done. And that might make sense for certain companies who kind of really need the performance, like finance companies doing high frequency trading kind of comes to mind. But for other companies like us, that cost is too prohibitive. So this is not going to work for us. So instead, our proposal is to kind of have like a hybrid solution where we kind of split the networking stack into two. We have a standard control plane path in the kernel where the headers go through the networking stack in the kernel as usual, and they get processed. And then the data goes straight into its destination inside of the user space host memory. And we kind of do this by two different parts. The first part is we set up the hardware such that we receive the packet payloads straight into its destination, and such that the SKBs end up in the sockets as per normal. And then the second part is, we're going to use IRU ring to read the SKBs out of the socket and get the data into user space in like a very efficient way. A quick primer about IRU ring. So IRU ring is a new way of doing asynchronous I/O in the kernel, and it does this by adding two different shared ring buffers between the kernel and the user. So there is a submission queue and a completion queue. So the way it works is, rather than making a syscall for every like receive or send, you instead prepare your requests called submission queue entries, and you prepare them, you write them into this shared ring buffer, the submission queue, and then you kind of kick the work off by entering the kernel, entering IRU ring via just one system call. Then the kernel does the work, services the requests as normal, and then for every request, it's gonna, once it's done, it's gonna post a completion into the completion ring, and then it's gonna return control back into user space, and then the user space can then proceed to go through the completion ring and process all the completions. Yeah, so the first step is to prepare the requests. I wrote some like code examples. So we first get the submission queue entry. We then call, there's a bunch of different helper methods that kind of prepares the request. And here we're preparing a receive request. So the kind of arguments are very similar to like a standard receive syscall. And then in doing so, we are already kind of moving the tail pointer for the submission queue. Then we kind of submit the work, we enter the kernel, this is a syscall, and there's a bunch of different ways to do it. In this particular case, the user is saying, okay, enter the kernel, and then I want to wait for a fixed number of completions. And then when you reach that number, please wake me up again so I can process the results. So at this point, the kernel's gone through the submission queue, it's done the work, and it's posted completions, control gets handed back into user space. And then the user space, there's a bunch of helpers as well for user space to kind of go through the completion ring and look at the results of each request. And then, yeah, once it's done, it calls this CQ advanced function to move the head pointer. All right, so next I'll talk about the design for our proposal. So like I mentioned earlier, the first step is to set up the receive in a way such that the packet payloads end up in user space memory, which is its intended destination. And we do this by essentially filling the hardware RX queues of a NIC with DMA addresses that point to user space memory as opposed to kernel memory. And once that's done, the rest kind of works on its own. We don't need to do anything else. And eventually, the SK buffs is going to end up in the socket, with the exception that the page frags are going to now refer to our user space pages as opposed to kernel pages. Cool. So yeah, the first step, the user space has to map some memory, and it has to provide it to IRU ring, register it. And IRU ring already has functionality to do this. It's called registered buffers. So this is pretty much unchanged. We're kind of reusing it as it is. So yeah, user space maps a bunch of memory and hands it over to IRU ring. IRU ring is then gonna pin those pages, and we're gonna end with a vector of these BRO. So after that, we want to then fill our hardware RX queues with these pages. And we do this by building something that's heavily inspired by the existing page pool. So for those who are not familiar, the page pool kind of initially started as a way of filling, or I think it started as a way for XDP, like a fast path for XDP, like to fill, to allocate pages. But it's kind of evolving into like a generic page allocator for NICs. And it basically just hands out pages to the NIC, and it does a bunch of management of those pages, ref counting and whatnot. So we kind of build like an equivalent, except rather than being backed by kernel memory, it's going to be backed by those user space pages that's just been registered with IOU ring. And in order for the driver to decide which one to use, we add a very thin shim layer that kind of looks at the QID and then makes a decision whether to allocate pages for a particular QID, using the zero copy page pool or by using the standard page pool. So once we've set up our hardware RX queues, we filled them with user space pages. We obviously don't want, well, we want very specific flows that correspond to the application we are trying to use this with. We only want flows from that to enter our zero copy queue, right? We don't want random flows to enter into them. And the way we do this is, well, we use two hardware features to do this. The first one, we use flow steering to kind of steer the flows that we want that correspond to our application. We want to steer those into the queue. And then we use RSS as well to exclude those queues from having other flows hashed into them, so that we only get the flows that we want into our zero copy queues. And we also only want the payload to end up in user space, right? We don't want to give user space access to the headers. So to do that, we use header splitting, such that only the payload ends up in user space. And I think typically, at least it's true for Broadcom, for header, like when header splitting is supported, we get two different hardware queues, right, per, I guess, QID. There's one for the headers and one for the payloads. And we only fill the payload hardware queue with user space pages. The headers are still filled from the page pool as before. So yeah, like I mentioned earlier, once it's set up, we don't need to really do anything else, right? The NIC just sees DMA addresses, except they now correspond to user space memory. So as it receives packets, header splitting happens, the payloads get DMA'd, so they only make one trip over PCIe and the main memory bus to its destination, and the headers get DMA'd into kernel memory, and then the SKBs get constructed, except the page frags now point to user space memory. Then those SKBs just travel through the networking stack as before. So this is really the one key advantage of our design. It's still going through the networking stack. You still get all of your visibility into the stack, all of your hooks and BPF and TC and QDisk and whatnot all gets handled by the kernel, and you still have all of those things. Except it has a more efficient data path. Oh, and we also mark these SKBs with a special flag, and we also set the UBuff as well, such that the networking stack doesn't try to copy it or do anything else with it. So like, it just leaves it alone. All right, so next we'll talk about how to actually get the data out of these, get the SKBs, our zero copy SKBs out of the sockets. And yeah, we do that with IOU ring. And we do that by adding more rings to IOU ring. We add two more rings. We add a RXQ ring, and we add a refill ring as well. And again, these are shared ring buffs between the kernel and the user. And you're going to get a pair of these for every hardware RXQ. And you can kind of think of them as like a proxy or making available in user space or giving user space access to the underlying hardware queues. And the RX queue is for user space to kind of receive data from the hardware queue. And the refill ring is a way for the user space to kind of give buffers back. All right, so the first stage is we want to submit a request. We want to submit a receive zero copy request. And this part is the same as normal. The user space prepares a submission queue entry and enters the kernel. And then the kernel is going to service the request by reading data from, reading SKBs from the socket. And in order to distinguish whether these page flags are user space or kernel, we tag them with a special cookie. And if we see the pages in the page flags of the SKB, if we see that they have this magic cookie, then we know we don't need to do any copying, right? The data is already there. So this is kind of only like a notification mechanism rather than a data movement mechanism. And essentially for each page flag that we see that is already in user space, we prepare a completion entry in the RX queue. This is one of the new queues that we added. So there's a one-to-one relationship between a page and an entry in this new RX queue. And you can see the structure of the completion entry in the RX queue. There is an offset, a length, and a region. So using that, the user space is going to be able to go kind of find where the data actually is. And then, yeah, there's another field for some flags. And then there's another field for which socket the data is actually in. And this is because we support multiple sockets for each hardware queue. So when the kernel's kind of either emptied all of the SKBs from the socket or it's reached some kind of read limit, we return control back into user space, and we write a completion entry in the main completion queue, so that the user space knows it has to go and look inside of the RX queue to find the data. Right, and now the user, upon getting the completion queue entry, the main completion queue entry, that will tell the user, okay, my data for my read request is in this specific RX queue. So the user space then goes through the RX queue. It finds the offset, the length, the region. That basically tells it, okay, my data for this particular packet is actually here. And then it can go and read the data, do as it pleases. And once it's done, we need to return that data back to the kernel, back to the driver, such that we can refill our hardware RX queue. And it does this through the refill ring. Pretty simple. It's just the offset, length, and region. And yeah, user space writes entries, prepares them, writes it into this refill queue. And at that point, the zero copy page pool that we added is going to be pulling entries out of this refill queue, right? So user space writes entries into the refill queue, and then when the driver is refilling its pages from the zero copy page pool, it's going to be then the zero copy page pool is then going to be pulling buffers out of the refill queue and try to keep it empty. So that's the consumer. All right, so that's kind of an overview of our design. And I'll show some early results that we got using this. So we measured the system bandwidth on a host with a Broadcom NIC that has 62 gigs of RAM, and we use IPERF3 as the benchmark, and we modify IPERF3 to use IOU ring and to use this zero copy API that we've added. And we measured the system bandwidth using, I guess, vendor provided measurement tools. So for AMD, it's UPROF. And we can see that the red line is without zero copy and the blue line is with zero copy. So we see, as expected, a significant drop in the overall system bandwidth. And I forgot to mention, this was at line rate at 25 gigs as well on the Broadcom NIC. So yeah, this is identical hardware, except it's with an Intel system, with an Intel Xeon. And yeah, we measure the memory bandwidth using PCM memory instead. And again, we see a significant drop as well in the overall system bandwidth. So one caveat here is that we turned off Intel DDIO. This is a CPU transparent hardware feature that tries to optimize the RX path by placing packets directly in CPU caches. We had to turn it off because it interferes with IPERF3. So IPERF3 is kind of like the ideal benchmark for DDIO. And yeah, so we turned off DDIO for these results. All right, so yeah, what's the status of this work if you're interested? We've posted V2, a V2 RFC on the mailing list. It's on both NetDev and IRU Ring. So please take a look and comment if you want to see the code and play with it. So that's one of the main things we added in the V2, right? So we initially only supported Broadcom hardware, like a very specific set of Broadcom hardware. But for V2, we added support in VF as well. And Pavel did most of that work. And this means that you can kind of play with I think the interesting part is with IRU Ring, and it allows you to kind of play with that part, try out the API, and see how it feels. So if you're interested, please go and try it. Oh yeah, and I mentioned, yeah, we in terms of real hardware, we only really support Broadcom at the moment. And I don't think you can even use it today because we depend on some out of tree changes from Broadcom. They haven't merged it yet. And then yeah, in V2 we also added multi-socket support, so you can associate multiple sockets per RX queue. And we also added copy fallback. So what happens when the memory region that you register for zero copy RX runs out? Before it would just crash, but now we have proper copy fallback. So we will copy into kernel memory and make sure that we don't crash when that happens. Right. And for future work, I mentioned how we kind of built this clone of a page pool. It's called the zero copy page pool. So Jakub has a RFC for the existing page pool. It's called a memory provider API, and essentially it's an API that allows you to plug in arbitrary backends to the page pool, and this kind of fits in really well with what we're trying to do, right? So you can imagine, rather than having our own custom zero copy page pool, rather than having this arguably ugly shim layer, right? That's going to require you to go and make changes in each driver that you want to support this in. We can just simply plug in as one of the backends for one of the memory provider backends for the page pool, and then the page pool can kind of handle the logic of deciding which backend to use for which hardware queue and whatnot, and that kind of really cleans up the design, right? We don't need to go and make changes in each and every driver. So yeah, that's kind of like the main thing we want to do for the next iteration of our patch set. We also want to add support for a proper testing device. So the hacks that we've done in VETH, it's not for merging. It's purely for testing. But we do want to add some proper test device, and we want to write proper self-tests. The other things that I kind of glossed over in this talk is the way that we do flow steering, the way that we kind of set up the NIC. It's very hacky. It's all kind of out of band using ethtool, and we would like to kind of integrate that into the work and streamline it, right? So you can kind of ideally associate the flow steering rules with a socket, which has a a 4 tuple of the source IP port, destination IPM port. So you can kind of like specifically set up and associate flow control rules with the socket. I think that would be much neater. And yeah, when we kind of set up the queue for zero copy, it's a very blunt way of doing it right now. So we have to bring down the whole device and bring it back up again. And yeah, we think it would be nice if we could dynamically do this on a per queue basis, right? So we don't need to, we don't need to bring down the whole device. And finally, we want to support GPU device memory as well. And for those of you who are not aware, Google is also doing something like this. They have a TCP dev memory proposal that does just that, right? It will, very similar to what we're doing, except the destination is in device memory. And we've talked with them. We're going to collaborate with them, and we are going to try and build on top of what they're doing for GPU support. And that's also like an interesting use case for what we're trying to do. So as I understand it, for AI machine learning clusters, while they may be very optimized in the back end, right, especially with NVIDIA GPUs using things like NVLink and RDMA, we see a lot of potential in the front-end network, right? How do you actually get the training data into this ML cluster? And you know, we see potential there for a for zero copy RX. All right, I'm right on time, so there's 5 minutes. Any Q&As, any questions? I'd love to kind of get your thoughts if you're interested. You know, what kind of applications do you see this being useful in? And then I'm also very interested in kind of like the user space API design as well.
Yeah, so you said you're setting up an the RX and the queue thing per hardware RX queue on the NIC
Yes.
for user space. So IRU ring now has my application starts up, I set everything up, and I have my submission, my completion queue, and now I have 48 other queues, like for like a thing with 24 RX queues or whatever, right? So like now I have to like go and figure out, I assume on the completion queue, you tell me which RX queue it's in, but like, what's the benefit of doing this instead of just having like one of each, right? Like, is there a way that in the kernel that you can just like do the multiplexing yourself? Like, okay, this hardware RX queue into like a single RX queue, or is there a reason you need to now that I now need to manage a billion extra IOU rings? Or ring buffers, rather.
Right. So we don't set up all of the RX queues for zero copy. So that's done on a per queue basis. Right. So there's an API to say, okay, I only want queue ID 0 to be set up for zero copy. Then we set up a pair of those refill and RX queues for that particular. Okay. So if you have 24 queues, nothing's going to happen until you kind of say, okay, I want to enable it for Q0 and 10 or something.
Okay, so the application then has to say, like, first of all, the application has to know what RX queue it's going to use.
Yeah.
And then allocate it, and then it's associated with that hardware queue.
Yeah.
Like, I see a lot of potential for users to fuck this up or just like constantly use RX0 because like they don't know, right? So like, is there a way that we can make this part like hide those details and be more optimal instead of letting the user?
Yeah, I see what you're saying. Yeah, I think in the ideal case, to make it really foolproof, you want to do all the registration in one go, like this queue, right? And then these flows and whatnot, right? I think on the networking side, we don't have the infrastructure to do that today. It's not fully integrated today, if that makes sense, because we can't do this dynamic queue management.
Right.
Yeah.
So so I guess that's the question I'm asking. Like, what does dynamic queue management look like? Is that a realistic goal to have short term, or is that like a long term thing? Or
yeah, I feel like it's a longer term thing that we don't want to explicitly depend on.
Okay.
Like, we don't want it to be a blocker for this patch set.
Oh, so I was also arguing that we should allocate the hardware queue dynamically, like not the user space specifying the index, but it just the kernel allocates some random queue for you. Should work, should be relatively simple.
So have microphone. So the only thing you basically need is page pool to allocate pages for you, which will also map in user space, the data portion.
I'm sorry, could you please
No, no.
repeat?
So
Yeah.
what the change? So the having an extra allocator on page pool makes sense, right?
Yes.
The change to the existing allocators we have is going to be you allocate those buffers or pages or fragments or whatever we're doing,
Yeah.
and you need to map them to user space as well for IOU ring to do the zero copy.
It's the other way around.
Yeah, the IOU
Yeah.
ring needs to. Okay.
Yeah.
Have you? So another thing that we do in page pool is that we manage to recycle those buffers. And
Yes.
I don't know if your network interface supports that, but that would be an interesting number to look at. What happens if you also recycle those zero copy buffers? And as far as the configuration is concerned, Jakub has a netlink patchet that we use to get stats, right? We can tweak that.
Yeah.
And we can use, you can set up the NIC at runtime basic. You can set up which use you need for zero copy, which use you need. You can even tweak the recycling capabilities because the recycling is just one function we call on the receive path. We can make that configurable.
Yeah, well, we can look into that, yeah.
So we can basically orchestrate the whole thing at runtime. Okay, you might have to bring down the interface. I don't know how much.
I think that's a big precursor, that kind of precludes runtime.
So in the context of stackable workload containers, right?
Yeah.
Do you think this page allocation can be accounted per container, or do you think we will be needing to, keep a separate pool of memory and then add more holdback to it?
Yeah, that's a really good question. We don't support containers. We don't support VMs today. We're not looking into that for the initial version. We're kind of assuming bare metal, right? You're just running your service, you're running your workload on a bare host, and you have access to the physical NIC. And then, yeah, I think once this version kind of gets into a state where it can be merged, we'll then look into, adding support for containers and VMs and whatnot. Yeah.
And at the very, the page allocations part of this is simple, that just works currently. So your space just does their thing and sends it up, and that's all accounted for in the normal C group stuff. So that for me is the least of my worries.
Yeah, the more interesting part is if you're using containers, you're using vETH or the new netkit that people mentioned in this conference, how we set up the queues and whatnot.
Last quick question, because we're running out of time. I'll go ahead.
Yeah, I'm wondering what it looks like on the IOMMU side. So as you map these pages in user space and for the receive queue and unmap them with are you keeping static? Are you redoing IOMMU config, or is this just still the NIC sees that map and it's just getting added and removed from user space? What does that end up looking like?
On the user space side, you mean?
From the device side view of memory, and also from user space, and how those are synchronized or not.
So are you asking how the pages are synchronized between user space and the device?
Yeah, I can catch you after if that's easier.
Okay. Yeah. Okay. All right. Thank you.
Thank you, David.
Yeah. Thank you.
I wasn't CC'd on that patchet, or I wasn't CC'd.
You might have not been CC'd. I don't think they were. Oh, man. Oh, I didn't use it. Oh, I thought you had an iron speaker. Then you were saying I could use it
I need to make a shirt that I know, I need to make a shirt that says or something. I just swear.
All right. Hello. Hello, everyone. I'm Zijian from ByteDance System Technologies and Engineering team. And today's topic is leverage Homa, enhancing Homa Linux for efficient RPC transportation. Here's the agenda. So firstly, I will give you a quick review of Homa, along with its limitations. And then I will talk about how we enhance Homa congestion control and stream RPC. And finally, I will talk about future improvements and conclusion. Let's begin. So why TCP is wrong for data center? TCP is designed for wide area networks. Its connections create high space and time overheads. Its stream orientation is awkward for applications which actually care about the delivery and the latency of messages instead of packets. Its fair scheduling increases tail latency for all message sizes. Its sender-driven congestion control ensures buffer occupancy at high loads. And it doesn't take advantage of in-network priorities. It requires in-order delivery, which restricts the opportunities for load balancing on both network hardware side and host software side. And here's the Homa. Homa is designed for data center networks with extremely low latencies. It's connectionless. There's no connection cost, no long life connection state. It's message-based protocol, which means on each returning of read in the applications can get a whole message. Homa tries to approximate SRPT, which is shortest remaining process time first on both sender and receiver side. And it also uses in-network priorities. It has receiver-driven packet scheduling for better usage of buffer. And finally, it has overcommitment for better throughput. Here's the overview of Homa. For senders, each outgoing message is divided into two parts: scheduled packets and unscheduled packets. Unscheduled packets can be sent blindly, while scheduled packets has to be sent when it gets explicit grant from receiver side. As for receivers, they will send grants wisely to prioritize short messages. So this is the overview of Homa, and then we will talk about more details. For the senders, for message less than unscheduled bytes, they will be sent blindly. For most of other messages, which is larger than unscheduled bytes, there's a pacer thread which monitors the NIC backlog and transmits packets from a throttled list to NIC in SRPT order. And when the packet is sent out, now is the moment for in-network priorities to take effect. Senders will assign appropriate priorities to the message according to the instruction from receivers, with appropriate short messages, with appropriate priorities for short messages. Short messages will bypass queued packets for long messages, which can avoid the head-of-line block in the middle of the network. And for the sender packet scheduling, it mostly depends on a configuration called RTT bytes. RTT bytes is a very important manually set config in Homa. In general, a sender must transmit enough bytes blindly to cover the round trip time to the receiver, including software overheads on both ends. During this time, the receiver can return explicit scheduling information to control future transmissions without introducing additional delays. We refer to this amount of data as RTT bytes, which is the length of the unscheduled packets. So after the receiver gets a data packet from the sender, it will collect information of the message, such as the total length and the remaining bytes of the message, and then send grants with RTT bytes to the sender with the shortest remaining bytes. And actually, the receiver doesn't only send one grant to the shortest message. It will send a limited number of grants to multiple senders. That's called overcommitment. The reason why we need overcommitment is that when the receiver sends a grant to a sender, the sender might not respond to the grant immediately because the granted message might not be the shortest one in the sender side, like sender one. In order to compensate for unresponsive senders and fully utilize the bandwidth, receivers will send limited number of grants to multiple peers. As a result, although some buffer might build up due to the overcommitment, it's good for the throughput. So that's all for the introduction of Homa, and then I will talk about the limitations. Homa has inefficient pipelining for large messages. Since Homa is a message-based protocol, while ensuring complete message delivery, it hinders efficient pipelining. As a result, for large RPC messages, Homa is not as good as TCP. And Homa does not have standard socket API interface, so it's not easy to integrate Homa into existing RPC network. And there's no long-lived RPC. For stream RPC, consisted of many Homa RPCs, which it will incur the overhead of creating and reclaiming multiple Homa RPCs. And Homa's performance is very sensitive to RTT bytes configuration. Fine-tuning this value is very crucial for Homa's optimal performance. But manually config this RTT bytes configuration on each machine can be very inconvenient. Currently, a single preset value is applied to all peers, which is not enough for diverse RTT and receiver downlink bandwidth. And Homa has weak congestion control when RTT is larger than 20 microseconds. With large RTT bytes will be a large value. As a result, most of the packets will be unscheduled packets. So the congestion control will malfunction. But in this time, if we lower the RTT bytes, it will not be able to cover RTT, and it's not good for the throughput. And Homa cannot coexist harmoniously with TCP. If we want to apply Homa in practice, we need to gradually transfer the traffic of TCP to Homa. It's unavoidable that Homa needs to coexist with other protocols. But Homa assumes that the bandwidth is totally used by itself. If the bandwidth is shared by other protocols, Homa may be over-generous on unscheduled bytes and over-grants scheduled bytes. And finally, Homa inactively handle incast. Homa assumes that the most severe forms of incast are predictable because they are self-inflicted by outgoing RPCs. And Homa assumes the incast where several machines simultaneously send requests to one server is rare. So Homa does very limited things to solve this problem. And here's the figure of the traffic congestion caused by incasting. When detecting congestion, it's essential to dynamically adjust the unscheduled window to prevent further congestion. So we think that static congestion window is insufficient because of the mentioned limitations. Currently, both unscheduled window and scheduled window are set by RTT bytes. However, they really need different values. For unscheduled bytes, it is used by the sender to define maximum bytes of packets allowed to be sent to a peer without permission. It is based on peer-side bandwidth and real-time RTT. Scheduled window is used by the receiver to define the number of bytes granting for scheduled bytes received by itself. It is based on local bandwidth and real-time RTT. As a result, a fixed one-for-all RTT bytes is not a good option. RTT bytes need to be dynamic. So then we will talk about how we enhance Homa congestion control. So here we try to address some of the issues with the new congestion control strategy. The dynamic per peer adjustable window algorithm consists of 3 parts: real-time peer RTT detection, RTT-informed congestion detection, and finally, adaptive window adjustments based on congestion. So firstly, for the RTT detection, we will try to send an RTT probe packet each 1 millisecond and calculate the RTT recent, which is the real-time RTT, according to the RTT probe response packet. RTT is affected by other traffic running on the same switch due to buffer sharing. In this process, we will also record the RTT minimum, which will be used for further window adjustment. And now we have the real-time peer RTT. We can use it as a reflection of the status of the network traffic. We define RTT low to be the low bound of RTT, which means there's no congestion, and RTT mid to be the midpoint of RTT to represent a fair amount of traffic, and RTT high as a sign of the congestion. And in theory, unscheduled window should be calculated by real-time RTT multiply peer link MBPS. But actually, in order to make the unscheduled window a more stable value, we use another value, RTT unscheduled, to calculate the unscheduled window. Basically, when there is no congestion, we give RTT unscheduled a relatively high value. When it's possible to have congestion, we linearly decrease the value of RTT unscheduled to a very small value. And here's a figure of the relationship between RTT recent and RTT schedule. And finally, we will use this value to calculate the real unscheduled window. And here is another heuristic optimization on sender side. The sender will maintain a variable called unscheduled ratio. If the ratio is less than 40% and the paether throttle list is not empty, which means the sender is busy with handling the scheduled bytes, we will adjust the unscheduled window to a smaller value. And now for receiver side, we set 3 times of RTT minimum to RTT grants and use this value to calculate the scheduled window. And now for scheduled window, instead of using peer link MBPS, we now use local link MBPS along with the RTT grant to calculate the scheduled window. RTT grant is kept at a relatively high value to make packets sent at a constant rate. It will help to reduce the P99 latency for large messages. So that's all for Homa congestion control enhancements. And we assume that this enhancements can help the Homa to be totally independent to RTT bytes configuration. Instead of fixed and static RTT, we now have real-time RTT. And this optimization can also help Homa harmoniously coexist with other protocols like TCP. Homa can be aware of the existence of other protocols traffic by feeling the turbulence of RTT. And now, Homa can actively handle incast. Incast can be reflected by high RTT, and then senders can adjust the unscheduled window dynamically. And then I will show you the result of this enhancement. Firstly, this is the environment of our testbed. We have an environment with 25 gigabits network and another environment with 100 gigabits network. We use the same workload in reference to do the test. Since Homa congestion control enhancements only have a trivial effect when message size is very small, we will focus on workload W4, W5, and other fixed size long messages. Test application is CP node. It's a program to test the performance, including throughput and latency for Homa or TCP. In our test, we mainly tweak some parameters for clients to adjust the behavior of the client node. Firstly, we will adjust workload, the workload to run the test, and then we will adjust ports for clients, the number of ports on which to send requests. And here's the setup of our basic performance. So we have one Homa server and one Homa client. So here's the figure of the throughput of basic performance in 25 gigabits network. In this figure, the axis represents the workload type, and the y-axis represents the throughput. The optimized Homa is able to make throughput performance increase about 5% to 18% for large messages in 25 gigabits network. And this figure is for throughput for 100 gigabits network. And likewise, the 25 gigabits network, the optimized Homa has 5% to 14% performance gain on large message throughput. And now for latency. On every workload, optimized Homa had slightly better latency compared with the vanilla one. And for 100 gigabits network, optimized Homa is better than vanilla Homa on nearly every workload. But for the last workload, the P50 of vanilla Homa is better than optimized Homa. But we have better P99 latency. Okay, so that's it for basic performance. And then we are going to test if our enhancements can solve the incast challenge. And here's the setup. So now we have one Homa server and 6 Homa clients to kind of simulate the incast, where multiple clients send requests to the server simultaneously. Here's the result. The main purpose of this test is to see whether optimized Homa can avoid buffer overlimit in the incast situation. Under the W5 workload conditions, the vanilla Homa has buffer overlimit, as you can see from the burst of the P99 latency. And in contrast, the optimized Homa can handle these challenges. And then we want to test if Homa can harmoniously coexist with TCP. In this test, we have one Homa server compared with one TCP server. And then in host B, we have 3 Homa clients and 3 TCP clients. We want to observe the impact of sharing Homa traffic with other protocols on the same NIC and switch ports. So here's the result. Under the same workload, optimized Homa paired with TCP has higher total throughput than vanilla Homa with TCP. The dynamic window adjust mechanism equips Homa with the ability to fill the traffic initiated by other protocols, dynamically regulating its window according to the network status. And here's the latency. Like the result of incast test, the optimized algorithm solves the buffer overlimit challenges under the W5 workload, whereas the traditional Homa protocol has significant latency burst due to buffer overlimit. And that's all for the Homa congestion control enhancements. And then we will talk about how we enhance Homa RPC, streaming RPC. So here's the figure shows how gRPC Homa supports stream RPC, which is defined as the function stream two-way in gRPC Homa. One single stream RPC consists of 7 Homa RPCs. This process includes 7 times of Homa RPC creation and reclamation, which incurs unignorable overhead and potential locking contention. And now we design a new Homa API. For clients to send requests in the same stream using the same Homa ID, we can help the client to reuse the same Homa ID to save the overhead of creating and reclaiming Homa RPCs. When the number of ongoing Homa RPCs is not high, the overhead of locking and the management of Homa RPCs can be ignored. However, under the heavy traffic load, when there are a lot of ongoing Homa RPCs, frequently creating and reclaiming Homa RPCs can incur unignorable overhead and exacerbate log contention. This optimization can alleviate this problem. And functional-wise, the optimization could also make the implementation of framework like gRPC to easily accommodate Homa transport protocol. So that's it for all of the enhancements. As for future improvements, we may need to improve our measurement for RTT. We need to distinguish between fabric delay, NIC delay, and software delay. Currently, we only measure the end-to-end delay. And we think we also need to optimize the dynamic window algorithm. If you have any thoughts, it's welcome. And we will also try to optimize pacer, and we will try to support zero copy on both sender side and receiver side. And we also need to do more tests for stream RPC enhancements to demonstrate our proposal. So for the conclusion, Homa is a very promising protocol in RPC context. Automatic and dynamic RTT bytes is a better choice than static RTT bytes. And our dynamic per peer adjustable window algorithm can improve performance on throughput and latency. And it can also help buffer overlimit resilience in the incast situation. And it can also help Homa be compatible with other protocols traffic like TCP. So any questions?
Great talk. So when you mean Homa can be used for RPC, you mean for intra data center traffic, right? What is the coexistence or with the enhanced Homa with long RTT flows?
Long RTT?
Yeah.
I mean, so for after we optimize Homa can better handle the long messages situation because of the dynamically adjust the window for long messages. Yeah.
Okay. No, but would the enough credits be shared between long RTT and short RTT, take into account the fairness of the difference in the RTTs as well, along with the congestion?
Yes, we will have different RTT bytes for different situations. Depends on the downlink speed. Yeah.
Okay. Got it.
And the real-time RTT.
Okay. And is this tested from between milliseconds and microseconds level flows, or within milliseconds is what?
Actually, this can be a configurable parameter decided by us or decided by your requirements. Yeah. Any other questions?
I have a question. There's no other questions. So in the case of the incast, the drops are on the downlink from the switch or in the NIC or where?
We assume the incast is in the downlink of the receiver.
So the switch or the NIC?
Should be the NIC, because Homa assumes that there will be no congestion in the core network. Yeah.
So what's the size of the buffer on the switch then, if that's where the drops are? Do you know?
Not sure about that.
Okay. All right. Thank you.
Right. Thank you.
All right. Next we have Vadim talking about clocks and synchronization.
Okay, let's get started. So, hello, my name is Vadim. I'm working at Meta.
I think, is the mic working? Can you?
Hello? It's good. Yeah. So, yeah, my name is Vadim. I'm working at Meta, and today I'm going to introduce you a new subsystem that will be available in the Linux kernel 6.7. It's called DPLL. It represents the devices, the DPL devices, which are digital phase lock loop. So we created this device, this subsystem. So yeah, let's talk about what's the phase lock loop system. Is like kind of simple devices which have a phase comparator, loop filter, and controlled oscillator and feedback path. And the main thing is that it has an output signal which is phase synchronized to the input one, and on the reverse path we have frequency divider or multiplier, and in this case you can just create a new frequency, the new output frequency, which will be phase aligned to the input signal. And the digital part here is the digitally controlled oscillator on the output, and again it also can be a digital filter or digital comparator. So again, the subsystem was created to be able to control and monitor this kind of devices. It slightly extends the pin part of PTP devices. Also, what we introduce here is the configuration of the priorities for the input signal, because the main problem here is to have a signal, output signal, which should be phase aligned to the input, but input signals can be different and can sometimes can disappear, for example. So the part of subsystem can provide you the interface to control the priorities of the different input signals and the monitoring part of the input situation. Also, it introduces special devices to mix the inputs and outputs. So in case if the DPL device doesn't have enough output or input pins, you can multiply by using a special external chip. So yeah, we did it on top of Netlink Transport. I think it's the easiest solution right now. So we created two separate objects. It's the DPL device itself. It has like common attributes like identification attributes, and then the mode, which can be automatic or manual selection of the input and output device pins, and the type, which is mostly difference between input frequency signals or recovered frequency from the SYN key device. And of course, we have monitoring attributes coming from Netlink messages, mostly about the log status of the DPL device, the phase offset, and the temperature, because the temperature is one of the main problems in the stability of the output frequency. So the pin object here also have an identification and the connection attributes, and it also has a labeling attributes because it's more about the external connections to the devices, and you have to identify what pin do you want to configure. And yeah, also every pin can potentially have different directions of the signal. So the same pin can be used for the input signal and for the output. So we have to configure it somehow. And state attributes also. So mostly devices can signal if they have something on the input device on the input pins, and we have a monitoring part of this. Yeah, of course, DPL devices have some limits on the output frequencies, and we added this attributes to the pins actually because again, configuration depends on the pins output, not only the DPL device. So some pins can have extended ranges of frequencies. Some can be like simple static inputs. So this is that's what we addressed. And of course, the connection attributes. So with this subsystem, we can create a really complex configuration of pins, which so we can connect an external pin to the DPL device directly, or you can do it through the MUX device, or it can be also the SYNC port, like Ethernet port, and recovered clock from the Ethernet. Yeah, and this is also an attribute to the pin. Yeah, so all the details are actually in the Linux kernel 3 right now. It's all merged, and all the netlink primitives and headers are automatically generated from the YAML schema, which is in the documentation part. And again, all the API is in the documentation. And we have a couple of drivers already implemented this DPL subsystem. So first of all, we will talk about what's the API. Yeah, the simple part is that for the DPL device itself, and we have only 4 operations that are supported right now. Only 2 of them are mandatory. So we have to the device have to provide the mode that's supported by the device and currently configured. Again, it's like PPS or EEC. And the log status get is also mandatory operation. It just provides the status information of the DPL device. For pin object is slightly different. It's a little bit more operations, so we have to be able to get or set a frequency, but again, it's not mandatory. Some devices can have fixed configuration of the pins. We also have direction changing stuff, but again, the change of direction of the pin is not mandatory. Just the status of the pin is mandatory to implement. Then we have state of the pin. It means if it's connected, if it's selected, or not. This is like the mandatory thing. And we also, if DPL device supports prioritization of the inputs, we also have special operations to set or get the priority of each particular pin. Yeah, and talking about the drivers, so we did implement it in our OCP tab driver for the time card created by the Meta. And a simple implementation, it just supports the BPS mode only and has a configuration of 4 external pins directly connected to the DPL device. And for now, the monitoring part is just the log status of the DPL device. And it's a simple example of how to implement it in the driver. But then we also have an implementation which is done by Judy for NVIDIA MLX5 driver. And now it supports EEC mode. It's SYN key stuff. And the whole configuration for the SYN key on the Ethernet port. And we also have a complex configuration, complex implementation of DPL device with like several DPL devices on the one physical board and different configuration of the same pins to the different DPL devices inside the Intel ICE driver, and it was implemented by Arkadiusz. And it also has support for SYN key configuration, but they also have external pins on the boards, so it can be switched back to the normal frequency mode. And the testing part is right now, we have RFC patches from Michal, again from Intel, to have the testing infrastructure for the DPL device, which doesn't need anything hardware related. It's just a, I would say, integration framework. Still have some questions for this patch set, but I hope it will be integrated into NetDevSim device that we have for the testing. Yeah, so have to say that it was a collaborative work with Intel, especially Arkadiusz, Michal, and Milena. And they proposed the separate objects for the pins because the first implementation was to have it all inside the DPL device. And yeah, again, as I said, they implemented DPL stuff in ICE driver. And also a lot of comments and work came from Judy from NVIDIA. I would like to highlight here the connection between net device and DPL device was totally done by him, and the MLX5 driver implementation too. So I believe that's it. So if you have any questions.
Hello. Do you have any additional monitoring or metrics on it beyond the temperature? So things like frequency or min-max offset type approach?
Yeah, we have phase offsets, so we can monitor it via netlink messages, the status of the device and the offsets of the output of the output frequency compared to the input one.
Perfect, thank you.
Football player, I'm not. So this is just curiosity, but the previous project and employer I had, we worked on a 5G thing where we needed SYN and so on. We're working with mostly Intel devices. And as of a year or so ago, the merge status of the drivers we needed for DPLL support and SYN were a little on the edge. So where are we right now in terms of Linux kernel version, and how much is upstream? And
everything is upstream right now.
Everything's upstream right now?
Yeah, everything is upstream, and it will be in the current release 6.7.
6.7?
Yeah.
Okay.
Any more questions?
No more questions?
Thank you, guys.
Thank you.
Yeah, now we have a break until 11:30.
Вчера прошло.
Ничего нормально.
Мы пошли в какую-то на забегаловку. Если заказал там коктейль Маргарита. Концентрированный синтез.
It was kind of cold when I first walked in.
I know. Sometimes I'm in it, especially. I guess you don't have to do it, but yeah, you can mark the figures one time. That's basically yeah, you have to send all the places where it starts. No, he knows everything. Well, I mean, it's not about faces, it's about the memory number, right? Yeah. I guess maybe on the reason that you acknowledge that you know that the code is unstable or something, so that you know, like, you're careful about the code. We got the news coming. The news is here. What is coming up? Oh, I think it's the Soft IRQ one. Yeah. Sebastian, do you know if he's here?
He's here, yeah.
I don't know. If he
Over
looks like-
there.
Oh, the long hair guy?
Yeah.
Maybe.
Yeah.
What exactly you mean by somebody?
What do you mean?
Pick up the type. Julian?
I don't know. I mean, it's not that it's somebody else.
I mean, we need to.
Yeah.
Yeah, probably it's me. Because I pushed this button, so nobody there are problems. There was problems with people, but
I mean,
yeah.
you're interested. You're interested. I mean, it's not. Not someone else.
What
I don't know, like, what was the feedback on the mailing list? Or?
Yeah, listen, probably because of security. It was this. Brilliant. Yeah, okay. All right, I think we can start. Next, we have Sebastian talking about Soft IRQ and RT.
Hi, my name is Sebastian Sivio. I'm talking here about the Soft IRQ problem we have in RT. It's not mostly correctness problem, it's optimization and from the workload point of view, which goes down the hill. Before we start, let me bring you up to speed how Soft IRQ works on RT compared to what you have in non-RT kernels. Basically, the whole thing is preemptible. We don't do hard IRQ. If you look at networking, for instance, we have this thread that runs the networking thread, the networking interrupt. And since it's a thread, it's preemptible. And preemptible means context switch is possible. So we could schedule out to user land. We can schedule out to a different interrupt thread. And in vanilla, you have this piggyback. So once the hard IRQ is done and someone raised the soft interrupt, then you switch to the soft interrupt at the end of the hard IRQ. So you continue going on with interrupts enabled, but you do only soft interrupts. And we don't have this on RT. We don't raise hard interrupts from, we don't raise soft interrupts from hard IRQ. Whenever this happens, it's usually exceptional. And this goes to K-soft IRQD. And this is a different problem. And since we are preemptible, this local BMH disable is required to act as a per-CPU lock, because we need to synchronize this interrupt versus the other, because all those things that may happen. As a result of this, the lock that we have in local bottom-half disable acts properly and all the resources are protected. The downside is that long-running threads block other interrupt threads that could be more important. They may have a higher priority assigned, and this is not considered. Also, you have tasklets, timers, and whatever soft IRQ-wise that is running thread up for some reasons. This also blocks threaded interrupts. And if you run soft interrupts on vanilla, what you have is that you do like 10 one round, and then you look, do I have this need reset bit set? And if you do this, then you just stop and continue K-soft IRQD for the iterations. But we don't do this in RT. The problem is that we have always RT priorities, and instead of setting the need reset, what you do is a PI boost. So we inherit a priority. And the intention is originally to promote the thread to a higher priority to get this thing done quicker and release the lock. But in terms of soft IRQ, this continues to run and continue to run as long as it can to complete all those things, and then it's done. And this is suboptimal. This is an output from SCAD tracer. I remove all the non-important parts, but the important thing is that you have the networking thread that basically raises the soft IRQ. And this wakes and continues to run. And then you have another interrupt, in this case, HACI for block I. And you see you have the wake of the thread, and then you have a SCAD switch. And within that thread, nothing happens except you give the priority to the networking thread, so you raise the priority. Lower number means higher priority, and then you switch back to networking again. And this continues to run until networking is done, and then you switch over once you release the lock. And then this is the earliest time that HACI, as in block, continues to do whatever it wants. So ideally, we would not continue doing networking, but hand over to block and do what it wants, and then continue networking where we left off. But for the locking reasons we cannot do that. So this is like an artificial case I made for, and we have other problems. For instance, you could have an FPGA driver, which you don't control from the kernel, but you only do in userland, and you only need the interrupt to wake up. And this interrupt would be like high prior, but it will be blocked for the bottom half reasons. And it's always hard to explain to people why do we need this. Also, if you would have a CAN driver, and you also need to inject like one packet into the stack that is forwarded over to user land. It's always hard to explain why do we need to wait until the whole networking stops doing whatever it does, and then we can inject the packet. And so the bottom half disable enable thing is basically to preserve the soft IRQ race and execute semantics. And from what I know, it's mostly per CPU resources that need protection that way. And so I've been working on a proof of concept to get rid of this global lock and make it smaller, like only the regions that need protection, that they get protected properly. And what I came up is a function called log nested PH. This is from after something we have already in the kernel called preempt disable nested. In MM and C groups wise code, we have sometimes a spin lock that is held, and the spin lock by itself disables preemption. But on RT, it doesn't. And there's code further down the road that relies on this preempt disable section, which is missing on RT. So that's where we have this preempt disable nested, just to ensure preemption is disabled only on RT, while non-RT just verifies that preemption was disabled earlier on. And so as I said, this thing disables then only, does the lock only on RT, while mainline is verified versus is bottom half really disabled. And the race soft IRQ and everything we had before is continuing to work as we had it. And not to add the locks like everywhere we need, like lock and unlock, we came up with a guard notation that Peter Tilstra introduced like one or two kernels releases ago. So this is what it would look like. This is from NAPIC Allocation. This is a per-CPU struct used in networking for SKB allocating. So basically, they have a page struct that is allocated once, and every allocation just borrows part of the page. And if it's empty, and it gets reloaded. But the point is, this operation is racy if it's interrupted in the wrong place. So instead of doing lock unlock, there's only a guard statement here, as you see it. And that guard statement does this lock nested BH, which is basically the lock only for RT for this particular resource, and invokes page frag rlog with that lock held. And once the return completes, the compiler automatically insert the unlock on its own. So there's nothing more to it. The other thing where you clearly see that the local BH disabled protected resource is netdef alloc SKB, mostly the same thing. And here we use the scope guard thingy, where you introduce a context where you have the lock unlock part for RT only, and it's limited to this part. So it basically moves the code to the side with the scope guard. One thing I identified also was this recursion thingy we have. Basically checks that if you recurse within the networking stack, you have an upper limit of 5 or 6 iterations before it assumes you loop indefinitely. On RT, the problem is if you get preempted, you can have 5 tasks, each of them increments the counter independently, resulting that it triggers the indefinitely lookup deadlock thingy. So for RT, we need to override it to have an owner, which has it, and a lock for the protection. So basically, this extends it a little bit, and then there is this part which basically checks if I'm the owner or if it's someone else. If it's someone else, we block on the counter. This is not ideal since we would PI boost other tasks using it, but I don't think it matters much from correctness point of view. Ideally, it would be per task, but I think this is way simpler, and it didn't bother us in the past. Next thing is BPF. The normal BPF part is, as far as I've been explained by few people, is already have their own logs for data structures and everything. So we should be fine if we do a BPF program and get interrupted. There are also some recursion checks for perf, trace, and so on. So this will continue to work as they do already. XDP is the only part that is missing things. if you do XCPU redirect, there are per CPU variables which have the state, how do you do the redirect? And then it may add things to the per CPU lists for the flush later on. So this needs to be protected if we get preempted midway. So this is like one thing for the flush, and then we need to tackle all the drivers. And fashion-wise, there are a few differences. Like this one would ideally get, so this is like the simple way, just guard at the beginning before you call into BPF, and once you return from the function, you have the unlock, and this is it. There are other drivers which only do the BPF run, but they don't do redirect. So then you can go for the scope guard and only protect the invocation, since you don't do redirect later on in the case switch later within the code. Ideally, to have everything together, you could move the XCP redirect return code upper to the function it's called, because the remaining part of the switch case is we don't care, we don't understand, we had an error and whatnot. So this is not required for protection. This would look different, but move the code around. Theoretically, we could have the guard at the top and keep everything as it is, unless there are like 2 drivers, I think, which do the flush within the switch statement. And with this change, this is what the same test case looks in the tracing. You see the networking driver starts doing its thing. The HCI driver comes up and wants to do something as well. It gets preempted. It does not wait for networking to finish. It does its thing right away. And once the block is done, it switches back to the networking driver, continue doing its thing. Like this is not limited to networking I/O. It's basically all force-fed interrupts and soft IRQ context work in general. Right, so this were the per CPU resources I've been looking at. This covers like 90% of what I've seen. There is this networking timer, which is special. And I've been looking at the history. It's been moved forth and back, and this is what we ended up as of today. The timer itself is made pinned, so it only fires on the one CPU we are on. And the caller of this function is mostly this. We allocate a timer at the front, then we disable bottom half, so the timer cannot fire because the bottom halves are disabled, so timer is deferred as well. And then we set up the structures, do the hash dance, which inserted in some kind of data structure. I mean, the comment says we're not allowed to touch it afterwards, but we still do it. I hope it's okay, but this is it. And I didn't add any logs here, but we would need some protection versus the timer. And I've been looking at it the last few weeks, and I think we could rework the whole thing, not to rely on the pin thing, and just set everything up, insert it, and then be good with it. Because most of the drivers are doing it. The pin timer are a minority in the kernel. There are only a few instances, and this is one of them. And right, the page pool we have, I've been talking to Elias while I've sent fix-ups earlier on. And the way it's been explained to me is that the page pool is safe because we only allocate memory in soft IRQ and put it back without any locking back to the pool in the fast path within the same soft IRQ context. There's no access within work queue or process context across CPU and anything else. So from that point of view, it should work basically. We had a few drivers got fixed in the meantime. So from RT point of view, it should be safe to accept it as is. And this is it. Do we like this guard thingy for per CPU protection?
The question is whether we are sure that we can identify all the bits and pieces which need re-entrancy protection if we drop the whole global or CPU global bottom half serialization. I mean, that's the thing which we need to worry about. And I mean, if this works out, then the next obvious question is, do we need the whole bottom half crap even outside of RT? I mean, we were debating this on and off, and we all know how good the heuristics work, which are involved there. They don't. But this might be a way forward. I don't know.
It does change a little bit how we design this, whether we just want to have because I think for RT we will make some sacrifices on performance, right? And it will be easier to accept the fixes that only are needed for RT versus if we look at it as like we're gonna deprecate entire Soft IRQ.
I don't think to make it mandatory for non-RT, but if we can put it in for RT and play with it and figure it out, it might be a way towards the more generic solution, which we all know how badly networking today suffers from the whole Soft IRQ concept already, because we have these. Okay, we do Soft IRQ processing for some time, and then block comes in and does Soft IRQ processing, and at some point you have to break out. But this all heuristics, I think we reverted 5 variants of that by now, and it never works correctly. So because it's always a workload which blows up. The main problem is that we have no way to schedule. The scheduler has no control because the BKL is the. I call local bottom half disabler per CPU BKL because the protection scope is as defined as we had with the big kernel lock. Nobody knows what it protects actually.
Right. But it switches out every so often, right? Like I mean, with the threaded NAPI stuff and with all the threading that we are adding, I think there's more and more people looking at how to get the scheduler to play appropriately for networking, especially with a bigger system with a larger number of CPUs. It looks like it might be possible in the next couple of years to figure out some way for the scheduler to schedule networking with sufficiently low latency. But for the threading stuff, we still depend on the local BH disable, right? Because we disable it, we get 64 packets, and then we we disable bottom halves, do 64 packets, and then we check whether we have to schedule out. So this is very different, right?
No, the point I'm trying to make is, I mean, you can do that with preempt disable too, and say preempt disable, preempt enable, or take a lock and whatever. It doesn't matter. I'm fine. The argument I'm trying to make, local bottom half disabled because it's not only for networking. It's used by timers, it's RCU, it's block, it's whatever. So you get this. But there's no reason why you would prevent block processing because you're doing network packet processing. There's no reason why you would prevent random HR timers going off just because you're in the network stack. The thing is, it's just saying, I'm owning the CPU. So it's both ways. So it also affects others. Whoever gains I own the CPU thing first controls the CPU and to the point where it gives it up, which might be good for some use cases, but it's not necessarily true. And the thing is, we don't have protection. It doesn't describe a protection scope. This is what bothers me. So what we did for other things where we have preempt disable, preempt enable pairs, we introduced this concept of local locks, which are basically compiling to preempt disable, enable in a non-RT kernel, and we can substitute a lock into it for RT kernels. But if you look at the code, it's actually entirely clear what the protection scope is. But preempt disable and local bottom half disable doesn't tell you anything. It's just, hey, I take something to make others go away. But what are you protecting? That's if you really want to go fully threaded and want to be more flexible on scheduling, you need to have the protection scopes and understand that. And I think this is a good way if we can start working on it from the RT perspective to break that up, because we are going to find the spots which actually need serialization, because most of the network stack is serialized anyway because it takes spin locks. Otherwise, it wouldn't work on SMP. So the only parts which are really crucial, I think, are the parts where you rely on a local button half, disable implicit semantics to protect poor CPU variables. And there, when we can find a protection scope for that, whatever the result is in the very end for a non-RT kernel doesn't matter, but it also gives you more insight into what are we doing here? Why are we disabling button halves, and why do we have to do that for half an hour instead of just doing it here because this is the crucial data structure to protect? So that's
but for non-RT, you're saying that would just be preempt disabled, right?
It could be preempt disabled, or at some point you could decide, hey, I just have a real spin lock there because it makes sense,
right.
whatever. Okay. I mean, that's not something we need to think about now. It's just, but once you have identified these scopes, you can think on the scope level what is the best thing to do, and it could be preempt disabled.
So, do we need some progressive push down to achieve that?
The question was, do we need a progressive push down? And I've been looking at all the per CPU variables that we have, and basically the only thing you can have is per CPU storage, because everything else that relies on bottom half disabled, and I found 2 drivers, are broken SMP as well. And at that point, it's not an RT issue for me because it's broken already. So you have per CPU variables, you have the pin timer, and this is it. I don't see any other issues. And the code I have for now, for non-RT, it's basically verifying lock-step-wise that bottom halves are disabled, and this is it.
But on non-RT, we have other issues. Like you pointed out the last time, the fact that some Soft IRQ networking code waiting for the completion of some timers. And because of that, we cannot have, for example, timers Soft IRQ preempting a networking Soft IRQ, for example.
Right, but this isn't affected.
Yeah,
the Soft IRQ will raise and fire as it would. Yeah. This is fine.
Yeah, I think it seems like a reasonable direction. Just a question of how to code it up nicely, right? So it looks pretty, and then we can start, scoping things.
Okay, so I mean, I would have to. Peter isn't aware of this, so Peter will. I need to sell the first few patterns to Peter, and then I come back to you guys.
What do you need from Peter?
The guard thing, the whole part for the locking.
Sorry.
The
guards. Yeah, the guards. Yeah. Well, yeah. Let's think about the guards.
I mean,
once you're familiar with them, maybe. But like,
the thing is,
this is my first time seeing them, and it looks like, yeah.
I mean, if you look at it from the XDP point of view, where you have you invoke the XDP BPF code, and then you have the switch case, and most of them have returned here, there, and there, and there. Then you have unlock at each and every iteration, and that way you just do the guard at the top, and you're done for the.
Yeah, for the XDP case, my one requirement would be we can't be changing the drivers. The drivers can't get more complicated because we're doing this. We need to figure out a way to lock it on the outside or somewhere in the XDP stuff, like internally, because I don't want to be changing every driver. It's too much.
Oh, I did that already. I think 40.
No, you did the flash checking, right? That was great, but you didn't have to change all the drivers. And here, I thought you were taking a guard around the call to inside the driver, weren't you?
Yeah, each one of them. Where are we?
Oh, I mean, you have patches in your tree, right? Because
not publicly, but yes.
All right. Okay.
I mean, this is the CPSW. Then we have. I mean, I gave just a few examples, but I covered them all.
Okay.
But isn't that code all mostly the same in all the drivers? So you could do a wrapper and have to
Yeah, we talked about it a couple of times, that they're all slightly different. We can try to pull out more of it.
I mean,
yeah.
I can send you the whole batch as one patch for the drivers, and then you take a look and yell at me what you want.
I looked at a couple of them and they were slightly different for no reason. So it's mostly copy and paste and then rearrange it and rename variable names or whatever and have some other data structure adding to it. So I think you could consolidate quite some of that stuff.
I mean, the point is that the network mapping and unmap and so on, the error case is different, so this differs from each and every one. But this concept we have here, that we have the BPF code and redirect as the next thing, so we can scope it together, and then the cleanup afterwards would look reasonable to me.
Yeah, I mean, this is perfectly fine to go into a common place.
So I would just show this is what I have.
Yeah.
And then you would say yes, no, this different.
Yeah.
No, I mean, the main question here was, I think, whether the network people are seeing any horrific problem with that approach going at least for RT for the moment.
I don't. We'll see what Eric thinks. He's not here, but let's start sending the patches and.
Okay.
Yeah.
Okay. Cheers.
Any other questions, comments? All right. Oh.
Just quickly as a heads up for the time wait stuff, I have a patch for that. Reverse the order of setting up the timer, and then I think we can remove the. We don't have disable. So.
Come again? I didn't get
the time wait thing.
Yes.
I have a patch that reverses the order in which the timer is set up and makes it unpinned because it was causing interference on isolated CPUs. So.
I haven't
should
looked
be
at it
covered.
yet, so this was my list. But if you have it, thank you.
Just as a heads up.
Okay, good. I'm behind you.
Seem to have two different variants of scope, guard, and just guard. Does it explode in an obvious way when you use the wrong one?
No, it doesn't matter. It's so guard is here, and when you have a return somewhere, you leave the scope block what, because you have an if, and then you have a guard, and you leave that if, you haven't returned the middle, then you have the unlock automatically added, and you have to have this scope guard, and it's something like you would do an explicit block in C.
Yeah, I'm just saying that often you start without the redirect, so you'd have just the playing guard, and then you'd later add code to add redirect. And if you don't know about these guards, you're not going to change to scoped guard. So you want it to clearly explode at compile time or run time to know you've messed it up. Will it do that?
No.
So how are you going to know you've got it wrong?
Well, it doesn't matter if you do scope
I'm talking
guard
about
or guard.
incremental development where you start off without the redirect,
I
and
think
later you decide to implement redirect and you need to change your guard.
But if so, we could just check in the called functions with a locked app or search whether they are held. So it explodes in your face then.
That's the best way.
Which is
Always
good
make
enough.
it explode.
Yeah, I mean, that's what locked app is for.
We take the lock inside BPF and then release it in the do redirect so that it's not in the driver.
Come again?
Take the lock when the BPF does a redirect and then release it in the do redirect. Daniel?
The thing is, the BPF run may access the CPU variable, and you need the same consistent state within redirect. So if you get preempted with another one, it's gone.
Right. So before you start touching it inside BPF, you take the lock, you start touching it, because the driver is required to basically do redirect if the program returns redirect. Okay. Well.
It kind of works, but it's really horrible because you return from a function with a lock held perhaps, and then you go into another function which releases the lock perhaps. That makes No, that violates my taste buds. No, actually, it's hard. I mean, you can do it, but it makes it hard. It makes it hard to get right. Harder than necessary, I think. We rather go and look at the drivers, how much we can standardize out this code, because the 5 I looked at, all the same code, just slightly different for no reason. So and if we have a common helper for that and fix up the call sites, then you have one place where we have to get the locking straight and not 50. And having the helper will also help new network drivers to get it wrong in the first place.
I think also at the NetConf we discussed to refactor those drivers and move the XTP stuff into the core, but that will probably happen after your work, because we're not
I
there
think
yet.
we should, that's a prerequisite as far as I can tell. All right, I think we are out of time, so thank you. Next talk is by Andy about crypto offloads, QUIC offload in particular. If you're not interested, this is the time to walk out.
But I'm sure everyone's very interested.
I think so. All right, take it away.
All right, great. Hope everybody can hear me, both here and online. I'm Andy Gospodarek. I work for Broadcom. This presentation, I'm sort of standing on the shoulders of giants here, Eric Davis and Eric Spada, listed alphabetically. They are key towards designing this, both from a software and hardware perspective. So I want to make sure they get their credit for really a lot of this. So mistakes are mine, good ideas are theirs. The other thing too is I know that there have been a lot of folks involved outside of Broadcom looking at this. There's a community around this sort of building up. So if you're interested at all in that, let me know. All right, okay, good, looks like we're rolling. Okay, so before we get going, I'll give a short overview of QUIC. I'm really trying hard not to say quick overview of QUIC over and over and over again. It's more challenging than you think when you see it right there. So the biggest thing to think about is that it's a transport protocol that runs over UDP. So if you've been coming to Linux Plumbers for a while, or if it's your first time, if you've been here coming for a while, I think it was in Santa Rosa a long time ago, so many years ago I can't remember. It was a presentation that was given by Google about like TCP fast open and sort of all the optimizations they've been making over time. And this, I think QUIC feels like a culmination of that from an outside perspective. And the idea is that HTTP 3 uses QUIC as a transport. And one of the key advantages to it is most of the stack runs in an application instead of running in the kernel. So iteration was able to happen really fast. And I think that's key to what got us to where we are today, but doesn't mean that has to be the future. So it utilizes TLS 1.3 for handshake and key exchange, as one might expect. And really the key components to think about is that transmit and receive connection IDs are how connections are distinct, how they are recognized. So this allows a lot of movement between source and destination IP. You can have sessions transition from one spot to another. So we'll talk a little bit more about these connection IDs, but these are key to the entire thing. And another key component is that in general, encryption is contained within each packet. In fact, there's even a little more to it than that. But the point is that you're not doing like a sending down a big chunk of data, expecting it to be packetized by the kernel and having it then expect to be received on the other end so it can all be put together and re-encrypted again. So you might wonder, like, why should I care about QUIC? That might be one of the things going through your mind, maybe not. So just yesterday, for fun, I did a quick Wireshark while we're sitting here. And apparently whatever properties I was visiting online during that time, 76% of the traffic was actually using QUIC. So whether you know it or not, it's really probably a pretty good chance most of your traffic is using QUIC as it is, or a lot of it is. Only 15% in this case was TCP. Notable 5% is ARP, so I guess there's a lot of ARP happening on the Wi-Fi here while we're here. That one was kind of humorous to me. But yeah, so QUIC is really heavily used right now, whether you realize it or not. If you've got a handset and you're, again, accessing many of the popular places online, you are using QUIC already. So of course, as a hardware vendor, we like to think that hardware offload is good, software only bad, in the most simple terms. And I've been working in hardware offload for a really long time, and I would tell you that this is mostly true, but there are certainly cases where it's not. And I think that one of the unique challenges with QUIC and one of the nice things that we could do if we support this as a community is that we don't need to necessarily offload every single thing to hardware. There's a lot of things we can still do in software that are fast. Ephemeral connections, short-term connections, small transfers, these are great for software only. Longer term stuff that runs for an extended period of time, pushes a lot of data, I don't know, streaming video, maybe that's a good option for doing hardware offload of QUIC. Depending on who you ask, some infrastructure will tell you they use as much as 15% of their CPU cycles just doing crypto. So you can do the math pretty easily on a multi-core system. 15% is a lot of cores that are spent doing something that could probably be done by hardware. So that's kind of our stand. The thinking about selectively where we can use hardware is a good idea. And if we think about NICs today, a lot of them have tons of hardware offload capability, whether it's stateful or stateless. Checksum offload, LRO. I can read these things off, but you all know about these. And some of them, as we move further down, like KTLS, there's a lot more stateful aspect to it. Many of these have support in the kernel for doing things like this. Many of them actually don't, and they're sort of a direct user space configuration. We sort of bypass the kernel. It's tough to think about, but there is no, GSO, or there is no like TSO if we think back to the original days. The kernel doesn't construct a bunch of TCP frames into one big giant frame to write down to hardware, right? We either get it from user space as a chunk, or we get it from user space in small pieces. So what would QUIC hardware offload look like in an ideal world? Or maybe in my world? So I think we would leverage our experience with KTLS offload and think about sort of the same APIs or similar APIs to support. The first way to think about it, I'm going to kind of go through what we've done and what we've been thinking about and what we've tried and talk about this. So I'm going to take a little bit of a bottom-up approach. I'm going to talk about the kernel first and come back to user space at the end, for those of you anxiously wondering what we're doing in user space. So the first proposal to think about is we would have a QUIC kernel module. We could also call this UDP crypto. We could call it whatever we wanted to, depending on how many different forms of UDP transport encryption we might want to support. The general idea is that we would have a northbound interface that speaks netlink that we'd use for control plane, and a driver interface, sort of southbound for lack of a better term, that would translate those netlink messages into a format that would allow drivers or hardware to offload. So if we have like a picture of that, essentially, because people love pictures, we have here in this one, this is the kernel and driver or hardware view of everything. We can think of this UDP socket layer. We have this QUIC mid layer that speaks directly to device drivers and assigns things. The two arrows, as you'll see as I show the user space later, the left represents what we would think of as control plane. So this would be netlink messages that come down. The one on the right should indicate socket. So we're sending packets, the actual data plane. So the biggest thing that we want to track with this kernel module is we'll track the flow in general. We'll track connection IDs, and we track direction, because just because you're offloading transmit doesn't mean you want to offload receive. Again, we want to leave this as something up to the application to do. Analogs to KTLS today, there's definitely a tracking of receive versus or offload of receive versus an offload of transmit. Additionally, we're going to, of course, track any of the session and crypto information for offload because that does need to be passed down through to hardware so it can perform the needed crypto. If we think about what could work, I can break this down. We can talk about these individual components, but we'd have what we call like a quick flow context. We could also have, again, this could be very generalized, but from QUIC standpoint, there's a configurable connection ID length from 0 to 20 bytes. We need to keep track of that. Need to keep track of connection IDs. Need to keep track of packet numbering. This is something that's also needed, probably needed, generally needed for all hardware offload. Where we are in the key phase, which crypto algorithm we're using, and then we've got one that's really a software and kernel construct I'll talk about a little bit more, which we'll think of XID or connection ID. Additionally, depending on which cipher you might choose to use for QUIC, we're going to end up keeping track of that as well. And this will be what's passed through when we go to the driver. So as I mentioned, we receive offload requests via netlink. So this is a little bit different than what we receive today. So if we think about KTLS, these are all socket options. But I think QUIC is much better suited because you essentially want to be able to control removing and deleting flows, not necessarily tying them specifically to an individual like TCP socket. Much better to have a way to do that out of band. So for example, if we have it over netlink, then of course there exists the example to say, well, why don't you show me what we have that's offloaded via QUIC? So in this particular demonstration of like a patched IP route 2, we've got an XID there at the beginning, our direction, receive, source and destination IPs and port numbers, the connection ID, the cipher that's used, and the device that's connected. I think it's really important and hopefully worth noting to everybody, we don't have a ton of other than the connection ID, we're not explicitly saying, let's show all the crypto information here. But I think this is a good way that you can tell, you can understand what's being done on your system right now. And again, if we're doing this over netlink, ultimately long-term, this is one of the nice benefits. Could also add these via netlink. I think that would be horrific because I think most of these flows are added pretty quickly in real time. So what you really want to do is, as I talk about with the user space in a few minutes, we'd have that a little bit higher up in the stack. All right, so the next thing we do is we think about, now we have this netlink messages come down, we have this database of information, this contained in our QUIC kernel module, and now we're going to add our offloaded connection information to drivers and ultimately down into hardware. So again, very similar APIs to what we've seen before. This is just a quick dev add, a new NDO that we'd propose, or I guess a TLS dev NDO we propose. Very similar in concept to what is with KTLS. We have the socket information, the quick flow context that I talked about earlier, as well as a direction. So anytime a flow is added, the proposal would be that an application notes that they want to offload a quick flow, netlink message is sent, driver handles it, kernel module, handles it, sends down a quick dev add. If successful, we see this message come back up, and a connection ID would be returned if the flow is capable of being offloaded. This connection ID is really key. It's the piece that ties everything together from user space all the way down to the driver. So we've talked a little bit about the kernel, gone through it pretty fast. Hopefully in people's minds, it's fairly clear. Let's talk a little bit about what the user space challenges are in the next pieces. So most of the QUIC implementations today, people have their own libraries. I think one of the reasons that QUIC was able to move and iterate so quickly and be successful is if you wanted to run QUIC via Chrome, for example, a new update of Chrome could come out. You've got your new QUIC iteration there. Any other app that you might have, laptop, phone, anything else that uses QUIC, new versions roll pretty fast. So you have this QUIC application and a QUIC library that many people use within it. As mentioned, the control plane is netlink. data plane uses regular socket APIs. So how do we do this? Application, again, initial handshake, setup, done. We're not doing any of this in the kernel. We're not doing any of this in hardware. We'll let the negotiation happen. There are multiple different types of QUIC frames, 1 RTT, 0 RTT. There are multiple different types of QUIC headers, long headers and short headers. It's likely that what we want to do is offload only the very basic and most regularly used ones. If you look at a QUIC connection that runs on your system, it becomes pretty clear. But if an application says, I want to offload, I know this is not an ephemeral connection, I know this is long running, it's going to be bulk transfer, I'm going to send a request to offload this to Netlink. Again, as I sort of hinted at, the application will get an XID back as part of the extended ACK cookie. We can store this. We can know now if we have to send anything on the transmitted data path, what happens. Oh, there we go. Okay, all right. So you put this XID in the C message header. If the data is to be encrypted by hardware, we'll know this. The kernel can handle this easily. Add an skbuff extension at the socket layer. I don't know why I keep looking. I have it here. Anyway, add an skbuff extension to the socket layer. And of course, the network driver can easily look at this XID, this XKBuff extension header, format any TX buffer descriptors that it needs to indicate that this is something that should be offloaded by hardware. And the hardware will send do the encryption and send the packet to the remote side, the peer. Like, sounds very simple in a lot of ways. There's clearly more to it that I'm sharing here in the slides, but it's not a difficult concept to really parse. Receive data path. I bet you can guess how this works. Not too different. So the frames will automatically be decrypted by hardware once you've done this Netlink call, and validation of the crypto to make sure that everything is fine will be reported in the buffer descriptor. Same kind of thing, buffer populates an skbuff extension with both the decryption and authentication status. As it traverses through the stack, the socket will set the C message header and pass that back to an application, indicating status and indicating whether or not the encryption was successful and whether or not anything needs to be done. So it's really kind of nice if we think about how we've done a lot of crypto offload, or not a lot of hardware device offload in the past. Again, I want to emphasize how important it is to let applications choose what they want to do the crypto. Choose whether or not they think something should be done in software or done in hardware. Because, surprisingly, typically the applications know best. We can spend a lot of time in the kernel guessing. Generally speaking, we're probably pretty wrong. As I mentioned, it sounds really simple. But it's probably not. Or we need to think about what the next steps are. And I'm flying through this, but that's all right. So I think like kind of the net takeaway that I've seen from doing this and working with Eric and others is that QUIC is really well suited for device offload, especially when we're thinking about 1 RTT frames and keeping short header packets involved. I think the modifications that we can make to the kernel and to network drivers are pretty clear. Again, we're standing, drafting behind a lot of what was done in the hard work zone with KTLS. Maybe the next slide comes. Too many slides. All right. What we will see is that QUIC device offload will be part of like driver updates for the BNXT-EN driver in hopefully the not too distant future. So this will be there. We can show patches. We can demonstrate the whole stack. We'll have it available for people to see. I think one of the challenges that when I think about this is what will the libraries look like? Will it take more time to increase adoption? I know from some discussions this week, there are support in OpenSSL for QUIC today. Do we want to do a Netlink support for that in OpenSSL? Does that make sense? Will that make it more usable? Do the primary consumers of this hardware or this driver or QUIC offload at all, do they want to use OpenSSL? Additionally, I've heard numerous people talk about QUIC in other contexts rather than typically like HTTP. I know that there's apparently an effort underway to do QUIC with SMB. So what would that look like? How would those SMB clients be able to integrate with the same thing? I think these are important questions to ask, but I think they're all, relatively speaking, they're pretty solvable. And that's all I've got. I'm hoping that there'll be some questions, maybe not. I see some folks right there. All right, bring it.
Can you elaborate some more? Like, so you mentioned earlier for the setup, you would need to use Netlink. Wouldn't it be easier for the user experience to just have like a set sock opt or whatever on the socket itself and then pass this down eventually to the NDO where you also pass the socket pointer? Because like I think like it would probably make the user experience nicer and also the adoption easier, right? As if everybody would have to build against the Netlink library and so on. So what what are your thoughts, or like why did you choose this path to go to via Netlink?
Yeah, I think decoupling, it feels like a decouple, like using Netlink feels like it's decoupling the data path and the control plane and the data plane a little bit. It's not really, because yes, it's the same set socket opt, but I think the hardest part is that there are I feel like it feels like Netlink is easier to use in some ways than the set sock opt. It feels like it's there's a little more introspection available. I mean, I think I would personally like to be able to say, can I see what's happening easily? Maybe I like Netlink. I could go either way. I do think that hold on, let's say, are there questions rolling? Okay. Yeah. So I also, the other notion that we talked about from some other folks as well is that, and I'm not reading the comments, I think today there doesn't exist the ability to delete flows with KTLS. The presumption is that the NDO to delete the flow is called when the socket is closed, because there's a one-to-one relationship between KTLS and the socket being open. So I think we need to have more fine-grained control. That would be a good thing for a little bit more investigation. Yeah.
So I work mostly across subsystems in the kernel, and the first thing I notice when someone creates a custom driver is why is there a custom solution instead of integrating that within a certain framework, within a certain kernel framework? So is there no existing framework in the kernel to accommodate this encryption offload without creating your own new user space interface?
I'm not sure I quite understand your question. I'm sorry.
Yeah. So my question is the use case of encryption offload hardware is already existing this is not the first protocol to do that, right?
Correct.
So my question is there already a framework that in the kernel that standardizes the user space interface for such a use case?
Standard maybe be a tough, like, is there a standard? I don't think so, really. I mean, right now, KTLS is the primary offload, I feel like exists when you percolate all the way down to hardware. I mean, there are other things that exist as, IPsec and other things that can be offloaded as well. But from a standard kernel interface, I feel like right now, KTLS is our example. And I don't know that I would call it like a custom driver per se. I mean, I feel like it's custom plumbing through the kernel, or it's plumbing through the kernel that, anybody could implement hardware that does quick offload. So I don't see this as something that hopefully we're the only people that would ever use. I would think this would be something that in the future multiple different devices today support KTLS offload. So the same could be true for QUIC. But there had to, someone had to do it the first time, and then everyone was able to sort of draft behind it. I hope that answers your question. Okay.
And how do you deal with the different ciphers that is used in QUIC? As far as I remember, the header is encrypted one way, and the data, the payload, can be encrypted in a different way. So how do you deal with the installation of these ciphers, and how do you deal with the data in hardware?
So I don't actually, I didn't think headers and data were encrypted differently. I'm not a QUIC expert, but
Oh, yeah.
the header is, huh?
Oh yeah, they are.
Okay. So I won't be able to specifically speak to the implementation, unfortunately.
Okay.
Sorry.
I was just kind of curious. I know QUIC is like another protocol level feature, which wasn't really mentioned, which was like the stream multiplexing. And I was wondering if that like complicated anything in the implementation, because it seems like you have to do some bind surgery in like the QUIC libraries to kind of just do the security, but not the multiplexing layer.
Yeah, so I think that's one of the, and I think the multiplexing is in like a later draft. Is that correct? Yeah, I think general agreement in the room, it's in a later draft. This really predominantly looks at like the first IET, looks at offloading 1RTT stuff from the original draft. So there's lots of things that are happening, right? Like people are encoding packet sizes or length sizes and connection IDs. All of that may or may not necessarily be supported in the first sort of implementation. So there's lots going on. I mean, even including, right, there's a like a load balancing spec or a load balancing draft that's being proposed for QUIC as well.
Yeah, I was wondering if you could speak at all to sort of per connection work that you would need to do for this. So what I'm thinking is, so let's say per connection you're offloading. If you have one connection, you're like pushing lots of data. Totally makes sense.
Yep.
But how closely do you think that matches current usage of QUIC? In terms of like, will people be setting up new connections all the time, and then every time you set up a new connection, you have various syscalls and netlink, configuration to be able to offload that, right?
And that is a great question. I mean, like I haven't deployed QUIC, so I don't know for sure. I think it's key to think that connections will be set up and torn down quickly, and some of them will be short and long. And I think that's part of the reason that we came to this, is that we do want to give the application provider the choice to do it. It's not a guarantee that just because you use a quarter or whatever of your CPU, or maybe not a quarter, but a lot of your CPUs on crypto doesn't mean you're going to be able to save all of that. We want to give people the opportunity to save as much as they can for longer flows, directional, whatever direction they choose, et cetera. So it's a great question.
Yeah. Maybe to speak to that a little more. I mean, I'm not a QUIC user, but I know that in cloud native, it's common to have a proxy, which will have like a whole bunch of connections that they're pooling, they're reusing those connections. So maybe on the server side, being able to offload something like this makes sense. I'm not entirely sure the semantics of the connection ID there, but it seems like maybe on the client side, like in your Chrome browser or something like that, it would be.
Yeah, that's predominantly where I see this. I don't see this as, we're not going to have quick offload on our handsets.
Yeah.
But or even laptops. But I think where it's most valuable, right, is absolutely where that connection is terminating. And then any intra data center traffic is probably also hugely able to benefit from this.
The IP crypto output you showed an IP address. Do you support quick mobility, or is some of the stuff based on like flow tuples?
So it should be. So we should be able to. We'll probably need to rewrite. Without going into too much detail, we probably need to rewrite that, remap the connection ID to a specific IP address as like a source IP changes, for example. There's no reason, right? I mean, QUIC supports just the ability to say the connection ID is all that matters. Whether I'm on my 5G or whether I'm on Wi-Fi, as it switches, the connection should stay up and should be operational. So that being able to detect that will probably have a miss or two.
Okay.
In hardware, and your application will need to say, hey, rewrite that source IP quickly. Sorry, see, there it is. You can't say it without rewrite that. And so the hardware I don't think we'll be able to support.
Okay.
Specifically, like, and I can't imagine. It's not I can't imagine. It remains to be seen. That really is how to do it.
Hi. Thank you for the great talk. I was wondering, have you considered how isolation will work in multi-tenant environments? For example, when you have multiple containers that want to use hardware offloading?
So I don't. Have we considered it? Like, no, it's not been a #1 thing that we've thought about. However, I don't know specifically what would prevent that from being possible. I mean, at some point there's, could there be scale issues depending on the number of flows or the number of connections? Yes. Do using containers make that greater? Could be. But I don't right now foresee a reason why it couldn't be an option.
Just in terms of performance isolation, for example, if you have one container impacting the performance of another application.
I'm sorry, can you speak into the mic a little more? I'm
in
sorry.
terms of performance isolation, or essentially when you have one container impacting the connections of another one.
That's probably that's a good question. It's good to think about. Like I have to think about that some more. I don't have a great answer. Sorry.
I think we're out of time. There's one more question from John on the chat. He asked if there's.
Oh no, John's not allowed to ask any questions. Okay. I'm just kidding. Sorry. Slide 13 is a quick ULP block. We're also working on using Sorry, I'm going to read that more slowly. John says, slide 13 is a quick ULP block. We've been working on using KTLS lately, and the SAT-SOC-OP interface is working nicely for us.
No, he does.
What do you have?
Is there any code to review, basically? Is there any code posted?
Not yet.
I mean, there was a. Is it going to be similar to the RFCs that were posted out of Meta?
Yeah, very similar.
Yeah, okay.
Very similar. So yeah, Meta's been involved in looking at QUIC offload as well. There was a patch series that was done last year, I think, maybe like a year ago.
I think that was posted, but that didn't include any offload. So yeah, not yet. Can you comment on? You mentioned that there is some work done on encoding the length of the connection ID. Is that as the next version of QUIC, or is that just some like best, some guidance, or like what's?
It's what people are doing. Like in order to save another couple bits in terms of communicating packet length that will encode the length. Like several vendors on their own version of QUIC will do this. So
it is being discussed at ITF, right? With all the.
I think so. Yeah. There's been discussions about next version. Like it's hard to know. Like is it a next version, or is it just an iteration? That part, like I can feel the breeze as that discussion happens, and that's about the extent of it.
All right, thank you,
John. We see your request, so for showing the code, we'll be there.
I can't hear you now. Go again.
Hello? Oh, yeah. Hello, my name is Stan. I work at Google in host networking team. And I'm going to talk a bit today about AFXDP and what we're proposing in terms of extending it to access the hardware metadata. I am assuming that maybe most people heard at least about AFXDP. But probably a lot of people don't know what the details are and how the user API looks like. So I'm going to spend maybe like 10-15 minutes of the talk just going through the AFXDP in general, what that is, because otherwise it would be hard to understand what the kind of the extensions are. Short introduction, it's AFXDP, it's a new protocol family. You can create a socket with AFXDP. It's kind of like a modern version of raw sockets or IF packet sockets. I guess the biggest selling point of the AFXDP is that it's designed from the ground up to be friendly towards zero copy use cases. It's also another, I guess, good thing is it plays nicely with the kernel compared to other bypassy solutions. One thing I want to point out is that I haven't invented it. I'm merely extending it with offloading. But if you want to learn more about the authors and description, here's the link to the documentation. But for me, I guess the name is a bit confusing because we have XDP and we have AFXDP. There's not a lot of XDP, to be honest, in AFXDP thing. So I have a short, I guess, picture that XDP is basically used as a flow steering mechanism. So if you want to use AFXDP, you usually install XDP program to kind of forward the packets to the AFXDP socket. Otherwise, they go to the regular kernel path with TCP/IP. I guess in theory, they might have been maybe in the future an implementation where the flow steering happens in the harbor and maybe AFXDP is somehow bound to the queue. But right now, basically XDP, the only function of XDP and AFXDP is to flow steer, which is gonna change with the things that we're proposing. Maybe also, if you read the docs and slides, there's always this XSK term, which is basically AFXDP socket. So don't get confused. Natural comparison of AFXDP is usually it's compared to DPDK. DPDK is a very known kind of kernel bypass system. It's I list some kind of comparison points here. Not all of them are true, or they used to be true, not true anymore. But in a sense, like DPDK is a bit more invasive. It's a true kernel bypass. They expose raw queues to the user space. There's all those user space in the drivers. Versus AFXDP, which kind of still tries to pretend that we're operating system and gives you nice abstracted queue format. Also, DPDK kind of by default, or originally it was supposed to be in the spinning core. And DPDK for most of workloads, I would say, is probably still slightly faster than AFXDP, because if you kind of bypass all the kernels, you can get all the benefits. But I don't think it's the gap is too big right now. So going forward, the way you basically use AFXDP socket is through the pair of rings and through a UMEM. So when you create a socket, you also create a UMEM, which is kind of user space memory chunk, where your payload will be received into and the payload that you want to send from. So you partition this UMEM chunk into some fixed sized packets, and you install this UMEM into the kernel. You kind of register the kernel. And then on the transmit side, there's a pair of ring. The transmit ring you fill in with the pointers to the UMEM, and then you get completions through the completion ring. On the receive side, it's a bit of the opposite. You fill in the fill ring, and then the kernel, as it receives the packet, it kind of moves the packets from the fill ring to the receive ring. And I have a bit more, I guess, detailed example. So for example, on I guess left, you have a UMEM with like 3 packet chunks, and you have empty rings. The blue ring, I kind of try to show that it's the ring that the user controls, because each ring has also a pair of producer and consumer indexes, and producer drives the ring, and then consumer kind of consumes the data from the ring. So initially, there's nothing in the rings. And then user space, when it wants to submit the packet, it can pick some UMEM chunk. It fills in the packet data with the PKT, and then it advances the producer pointer. And then whenever kernel is done with the transmission, it kind of advances completion ring as well and points to the same packet. Similar thing is happening on the receive, but again, with receive, we kind of pre-fill the fill ring. The user space basically tells the kernel that I am expecting the packets to arrive into those UMEM chunks. And then the kernel, when it receives the packet, it fills in the payload, and then it moves the receive ring pointer. Going back to the XDP parts of the AFXDP, this is a small example of how you move the packets into those rings. So you have to create a BPF program, you have to create a XSK map, which kind of abstracts the AFXDP socket. And then in your XDP program, you have to basically call this helper BPF redirect map, and you say that you want to forward those packets to the AFXDP socket. In the real world, you usually also have some, I don't know, flow filtering or something, because currently the program will forward all packets to the socket and then nothing will come out of it. So I guess this is, I'm mostly done with the introduction, and we're coming to the part where our extension come in. So what is missing from this picture? So I guess technically nothing from the high level overview, but as you can see, the only thing that you can pass to and from the kernel are just raw payloads. And modern NIC hardware, it is much more capable. When you receive the packet, it gives you a bunch of metadata. I don't think we have a good term for that. There's metadata, hints, offloads. They both have been used interchangeably. But the point is, for example, when you receive the packet, what NIC can do, it can also verify the L4 checksum for you. And it can pass this extra information through some descriptor field saying the checksum is okay or not. It can also compute flow hashes for you. It can also communicate you things like a real receive harbor timestamp. So if you want to know how your packet flows through the stack, you can kind of timestamp it at various places. And this is one of the places that the harbor gives you an opportunity to do so. On the transmit side, it's also very important because this has been used in the kernel for a long time, but things like when you send the packet, you don't want to spend CPU cycles calculating checksums. So what you can do instead, if the NIC supports it, you can actually ask it that starting from this specific position in the packet, I want NIC to checksum everything and put this checksum into some specific offset. The same on transmit, one of the things that you can also ask for is maybe at completion time, you can ask the NIC to give you the timestamp on when the NIC actually put the packet on the wire, because it might sit in the queue and you don't know, but you can ask it to kind of give you the hint. Yeah, and as I mentioned, we don't have a good solid name for it. So if you read the docs or look other slides, don't get confused. It's like metadata and hints. So maybe more about AFXDP implementations in general. One of the big things that I think has been preventing its adoption, and the one that has been solved not by me recently, but it's about using larger MTUs, and it's about using scatter-gather lists. Because when you want to send a packet larger than 4K, there was no way. The whole UMM, it's like page-sized, and there was no way to kind of specify multiple chunks. With recent work for scatter-gather, you can actually now reference multiple chunks of the packet when you're sending it out. This is very useful, for example, I don't know, things like tunneling offload. So when you need to add some when you receive the packet and you want to send it forward somewhere else and apply the tunneling, in the old world, you would have to basically copy the payload in and out. And now you can just insert small chunk with the tunneling information and then basically reuse the packet payload. The things that I am focusing on is on receive pass, there was no way to access the offloads, but this has been solved by me recently in the 6.3. The code is already there. On the transmit path, we're still kind of discussing on the list. I think we're pretty close to the final solution, but I'm still going to talk about this here. So yeah, more details about receive side and how it's done. So what we've added is we basically added the ability from the XDP program to read those offloads. So those offloads, they're not they're not like super flexible. There is a specific set of the offloads that we support right now. This set can grow, but we do support this set by having a bunch of predefined k-funcs that you can call in the XDP program to access particular offload. For example, for XDP BPF metadata receive timestamp, you call this helper, and it will put the receive timestamp. Same for receive hash. The k-func, it has per device implementation, and it will go into descriptors and pull out the relevant information. The good thing is that those k-funcs, they give you kind of generic API on top of all NICs. The bad thing is like not all NICs are super uniform. So there's like a balance to have in terms of what is accessible. The way that you would consume those metadata information in the AFXDP receiver, though, is a bit, I guess, maybe complicated or flexible. What you can do is, in the UMEM chunk, you can reserve a fixed headroom for every packet. Let's say you reserve, I don't know, like 16 bytes. And then in those 16 bytes, you would do what you would call as, you would hold those helpers in the XDP program, and you would put at some specific offsets the metadata that you care about. Because what usually happens is there is, when you're using AFXDP, you also usually ship your BPF program. So there's kind of a contract between the BPF program, metadata area layout, and AFXDP consumer layout. Oops. This is what it would look like in terms of code. I have on the top, I have at the top, I have XDP program. What it does, it basically reserves this headroom. It reserves 8 bytes of the headroom, and then it calls the BPF XDP metadata RX timestamp and points to this headroom. This helper will go ahead and fill out the timestamp, and then you would redirect the packet to the AFXDP socket. And then bottom 3 lines are, it's the user space code. So what you would do is you would call this XSK UMEM get data function to get the pointer to the payload. But then you would have to kind of offset into the headroom a bit to access the timestamp. So on the transmit side is a bit different because on transmit we don't really have XDP. So the approach, I would say, it's less flexible, but it's also, I guess, more user-friendly. Initially, I tried to add some lightweight XDP hooks at TX, but there was a lot of kind of uncertainty. How would they work in SKB path and non-SKB path? So we decided to settle on just fixed format, where we have a fixed UAPI between the kernel and the user space. And this format of this headroom is kind of a struct that has some fixed layout. Yeah, and this is the picture. Basically, it's kind of like receive side, but instead of the headroom being whatever the BPF program decides, you have to put struct XSKTX metadata. This struct is in the UAPI headers, and basically the kernel and the user space, they have to agree on how it looks like. And in terms of code sample, this is how you would use it. You would again call the same XSK UMEM get data. You would get the payload pointer. From the payload pointer, you offset to the left to get to the metadata. And in the metadata, you would say, if you want to use, for example, checksum offload, you would say, you would add a flag saying, I'm requesting checksum offload. And checksum offload kind of API is the same as the SKB checksum offload, where checksum start points to the point after which you want to start calculating the checksum. And the checksum offset is the point from the checksum start where you want to put the final checksum. For me, it was originally very confusing that the offset is from the start, but I guess it is what it is. I'm preserving the same APIs we have in the kernel. And kind of summarizing it all, receive side is already in the kernel. Receive side we have 2 offloads supported currently right now. It's timestamp and it's receive hash. Transmit side, it's still on the list. There's still some small discussion, but I hope we can wrap it up and have it done soon. On transmit side, we give also access to the transmit completion timestamp, and we show an example of how to support TCP UDP transmit checksum offloads. I would say that the rest of the offloads should also arrive in the future, because both receive and transmit, they kind of provide the framework of how to do the offloads. So it should be relatively easy to extend it even more. And speaking of extending, a couple of things that have been flowing through the list. There's already a bunch of patches to add VLAN receive offload support. I don't think there's like a super big consensus of whether it's needed or not, but it's just one of the examples of how to extend this the framework. The patch series was also originally containing the receive checksum offloads, but I think it was dropped to make it easier to do just the VLAN part. So hopefully once the VLAN part is done, we can go back to receive checksum. Because yeah, receive checksum is one of the offloads that are kind of super useful. On the transmit side, also what's going on in the future, I already have kind of private patches from Song about transmit departure time. This kind of departure time, I don't know, probably also people familiar about the whole timing wheel approach, where the idea is to move from the queues to some timing wheel implementation, and the departure time basically means that when you're sending the packet to the NIC, you're saying that, oh, don't send it out right now, send it out sometime in the future. This is very useful for like doing pacing and stuff. Other things that might be useful on transmit are crypto offloads, and for us is like particularly PSP, when and if it lands. Another thing that might be useful is like segmentation offloads. I don't think TCP is particularly useful. Maybe UDP is more useful because like for quick things on the edge, it might be useful to chunk packets up. But for TCP, I don't know, there's been some concerns about whether it's really useful or not. But again, it might not be specific to TCP or UDP. Maybe there is some generic segmentation offload that we can do. Yeah, and I think that's probably mostly it from me. I want to thank a lot about the upstream reviewers. I didn't list them all here, but there's been a lot of people doing reviews, giving feedback. There was also a lot of prior kind of art in terms of receive offloads. There was a different patch series that tried different approaches. So yeah, and if you've tried AFXDP in the past and got bitten by the limitations, now might be a good time to reevaluate and see if you can use it again. Yeah. Thank you.
Thanks for your talk. We are actually moving our QUIC implementation to XDP. So the TX crypto offloading is very important even for QUIC, at least for us. Yeah. So and I have some questions. So what kind of driver support does this all this kind of work require? Because I believe at least the checksum offloading also requires driver support. So what kind of driver do we already support this?
Yes, that is a very good point. If we have people doing drivers and vendors, please try to incentivize your employers to add the supports. Yes, because all those require driver supports. Right now, I think I did Mellanox and we have something from Intel. But yeah, again, my hope is that most of the stuff can be extended easily because SKB already uses all this infrastructure, right? That's nothing new. It's like we're just giving a different interface through AFXDP. So yeah, if you need that, maybe try to also contribute if you have specific NIC.
So what is the interface to get the TX timestamp back?
It basically reuses the same headroom and it puts it back in the same area.
Okay, and then you know when it was sent and you still grab into the same memory.
Right. Basically, you have the UMEM chunk. In the headroom, you have the flags where you request the timestamp. And then you put this UMEM in transmit ring. And then when the kernel is done, it's basically in the completion ring. It points to the same UMEM, but at some specific offset, it writes you also the timestamp.
Okay, I see. Okay, thanks.
Time to get some food.
All right, thank you. Do you want to hold on to these for the break?
I've tried it out. And this is actually all feature that we use for a long time. Yeah.
Sounds like you got some good guys in those rooms. Yeah. This lady.
And then Tilly's running around there and just kept knocking down.
I haven't been down there, so I don't know. Normally, no, we'll be there. It's usually there till 1:30.
Have more flexibility in the end. For example, things like actually TX filtering, for example. So you send whatever XDP sockets and you send data, but you don't want applications that you have maybe untrusted applications running and they think data still
Should we go ahead and get started? All right, sounds good. All right, welcome to my presentation on Connect. Why are you so slow? My name is Frederick Lawler. I work at Cloudflare as a systems engineer. I am most known for my kernel work on the security hook for the create user namespace, a traffic control. Well, I didn't cause the CVE, but I certainly fixed it for the traffic control, no queue. And I'm also known for the PCI print K macros littered about in the PCI subsystem. So before we really dive into this talk, we really want to talk about some of the one of the unique cases that we have at Cloudflare in terms of uncached resources and why we make so many connections out to perhaps a single origin. We're going to start there, and then we're going to dive into a little bit about the Connect algorithm, specifically inet hash connect, and then we're going to follow up with some solutions that we kind of came up with to solve this problem for our case. So for uncached resources, we typically have this flow. It's very simplistic. We don't really have a concept of an end user, considering that it's pretty relative to where caches or where assets are served from. So we tend to call our end users eyeballs because people have eyeballs and they're looking up an asset. So the request typically goes into our Cloudflare network. It eventually arrives at some colo location and on a machine that runs this frontline service that we just initialized with FL. FL then picks another metal within the same colo to actually to pick a cache service that will actually send the request out to the origin to fetch the asset to bring it all the way back to the eyeball. And this is our typical workflow for uncached assets. So this talk is going to be primarily about how do we optimize this problem for us here at Cloudflare. So the way this works is that our metals or servers, however you want to call them, are typically set with a port range of about 56,000 imperial ports. And the way we leverage these ports to establish many connections is we have this basic socket for TCP. We set the bind IP address no port socket option. And then obviously we bind the source IP that we want to connect with, and then obviously make the connection afterwards. So the reason why we do this is because we want to enable us to pick IP addresses in which we would serve or fetch these assets from. And this can be useful for a variety of reasons. Say trust reasons is just one trivial example. It's always nice to know that our customers know that requests are coming from us, right? So we can be in their allow list, things like that. And we have a link here that kind of goes more in depth into some of the reasons why we eventually picked it. But the most important thing to take away from this pattern is we're late binding a port as we do a connect. So we're not binding a port immediately. We're waiting until we actually make our actual connection to bind that port. So we get something like this. I know it's a little hard to see, but we actually saw a spike in May of about 50,000 requests out to a single origin. So this particular customer had a really unlucky day with us, but not all for loss, right? We typically have 2 IP addresses that we assign to our CAS service to perform this these sort of connections. And that 50,000 connections are actually split between these two. So we kind of do like a little load balancing trick with that. So it's not all bad. So in reality, we're about sending, in total to this single destination, we're sending the 56,000 or 50,000 connections. But in reality, we're on our end, it's split to maybe 28,000, right? So when we took a function latency of a synthetic workload to kind of profile how this might look, we can see that we have a little bit of a bimodal distribution. We have the fast path on the y-axis is the time in milliseconds or nanoseconds, sorry, that it takes to establish a connection, but not like establish. We're not talking about back and forth. We're just talking about this strict connect syscall in this case. And on the x-axis, we have the amount of connections that we're making. So in this example, we've modified work, which is a nice little tool to stress test your applications. And we set that to try to keep around 70,000 connections active at any given point, because they come up, they come down, just fill them in as much as possible, and we get this bimodal distribution. But we actually want to use one IP address. So when we actually load balance between the two, we saw that with 2 IP addresses, it's somewhat okay, but with one, and well, I'm jumping ahead, but the reason why we want one IP address is because IP addresses are getting prohibitively expensive, right? This is, I realize this is an old chart. We just wanted to show the, over time, the cost of IP addresses over 2022. And I've checked for the last year, and it's around roughly $30 an IP. So on the y-axis, we have the amount of money, and on the x, the time. And so when we actually look at one IP address, our bimodal distribution becomes even more pronounced. So we see that about half of the connections are in the fast case, and the other half are in the slow case. And for fun, we tried with 3 IP addresses. And this is the really interesting part, is that the more IP addresses we have, the faster this becomes. And this is due to the load balancing, and we'll get into that a little bit later. So this is fine for most workloads, but for Cloudflare, our customers are still largely IPv4. And we want to achieve similar performance with one IPv4 address as we see with 3 IPs. And we want to leverage our infrastructure to lazily hand off these connections in the slow case, right? We want to fail fast. We want to be able to say, we have no more ports available. We cannot make any more connections. Send it off to the next metal. So it's time to investigate a little bit about why that is. We took a flame graph of a typical production server. This is not representative of any of the data in this slide or in this presentation going forward, but this is a typical representation here. So we wanted to kind of see like what are our culprits that might provide this an explanation for our bimodal distribution. It might be a little bit hard to see, but we can see that the most amount of time is spent in the inet hash connect function. And then that's further broken down into the inet check established. And then we have some lock intention. And this is pretty typical for our metals. So diving in a little bit deeper into the inet hash connect. So it's important to remember that this function is called for both the IPv4.6 and the IPv6 case. And we assume that the kernel always has to pick a port. So going forward, we have to make that assumption. And the way it works is that the inet hash connect function will make a call into secure IPv4 port ephemeral to get a hash, passes that back up into the hash connect, and then that passes it down to the __ inet hash connect function. And then in between there, we start looping over the ports, and we call the INET check established when we find a port and we try to bind to it. So this is kind of what it looks like in code form. I greatly reduced this down because there is a lot more there that is not currently shown. But for simplicity's sake, this is basically the crux of the algorithm. We'll take a look at it one by one. So first off, we try to grab an offset, and this offset is provided by that function that generates this hash. Now I removed the slides for this because for sake of time, I figure it'd be better if we just skip going into proving why the randomization is good. Trust me, it's good. So what we do is we first get a random offset, and then we add that to the low port of our IP local port range. So the very first port. In this case, it's 9024 for us. So it's the random offset plus that, and then we have our first port to look at. Now, before I dive into the loop, we're going to talk a little bit about this loop right here and why this may or may not be an issue for us. So in the INET check established, so in our test cases, we are looking at a very not chatty system. So we don't really have many ports already bound by this point in our testing. So we can kind of rule this out as a problem. I know in the flame graph we can see that that this actually produced a bigger problem, but this only really becomes a problem when we have too many connections going in anyway. So like if you have multiple destinations, things like that, it's all unique. This starts to fill up pretty quickly. So then it does become a problem later on. But for the sake of this presentation, we're mainly focused on very minimum system to test all this stuff. And if you're curious about and want to learn more about how ports are picked and how the bind buckets work and all that fun stuff, we have a link right here to quantum state of the TCP port. Now it's time for the loop. So the way it works is first we loop over half of our ephemeral port range, and then we loop over the half one for each and every single connection. And the way this works, or I should say looks, is in this case right here, we have a system with, let's see, 8 sockets. And it's pretty, it can be a little confusing at first, but essentially we have our offset, and then we add that to our low port. And in the socket case 0, we're at port 0, so we're going to go ahead and pick it, right? On next socket, again, we have another randomization, and then we just happen to pick port 4. But where it starts to get interesting is on the third socket, we start off at the same offset as the socket before it, but because that port's already taken, then it goes to the next one. And we do that a few more times, and eventually, when you're in the latter half of the port range, we get into a case here at the bottom where now we're looping over all the even ports first, and then we're adding to the offset to get the next odd one, and then now we're looping over all those to pick a port. So there's a lot of looping involved. So is the loop a problem? So we've kind of verified this through mostly experimentation. Going forward, all the charts that we'll be looking at kind of look like this. All the green dots are even ports. All the red dots are odd ports, and the reason is because of this low port plus offset. So if the low port is even, it's always we're always going to start at the even range and then go to odd. But if it was an odd, you'd always start at the odd range and then go to even. So this can kind of go back and forth. And what we see is when we open up 56,000 connections, which is the total range of our system, that can take an upwards of 3 minutes for us to do, with an overall average of 279 connections per second, which is not great. We expect our systems to be able to do a lot more than that. So in our conclusion, we kind of figured that the main problem with the main explanation for this bimodal distribution must be the looping. And this is evidenced by an earlier patch that was submitted. This person tried to make an attempt to keep track of when ports start parity switching over into the other port range, and then just immediately start doing that once all the even ports are taken up. Unfortunately, it was not merged. And I've included a little slide here to kind of give you guys some example to toy around with in your own, your own machines. If you're experiencing slow connection times, you can use this little BPF script. I mean, it is networking and BPF track. We're making the assumption here that that your port range also starts even. So we're only tracking when we do the actual port parity. A trivial rate can kind of tell you which task and which C group you know, kind of reach this point and, you know, just keep track of that. And I've also included a link to our Prometheus eBPF exporter to keep track of that information in Prometheus. So what do we do? So we're going to start off with some feasible but not viable solutions for us. We can try to split the egress unicast connections over multiple IP addresses. Again, we're already doing this with at least 2, but we want to move down to 1, right? We can introduce a system CTL to manipulate the connect, which was already attempted. It's still viable. You can do it yourself. Or we can pick a random port in user space and then just bind with that. We'll talk a little bit more about that. And then we can leverage this new IP local port range socket option, which allows us to define a local port range per each connection that we would like to make. So splitting egress unicast connections over 2 or more IP addresses. So some of the problems that we have identified with this approach is that we don't necessarily want to leak our networking configuration to user space. It would be nice if the kernel could have some sort of ability where we can define IP addresses that we can load balance on interfaces. This would be a nice feature so we don't have to leak this information, for instance. It does require the IP bind address no port socket option, bind before connect pattern, and we do this strategy now, but we still want 1 IP address. You can introduce the system CTL to manipulate this. Now, this does require kernel modification. Again, the patch was submitted, and the main reason why this patch was submitted was because it doesn't cover the vast majority of use cases, right? So the way it worked was you try to have some volatile variable defined somewhere in this inet hash connect.c file or something like that. I forget the exact file name. But you have this volatile variable there, and you just keep track of when this occurs. But the way the loop works, and we can take a look at the code later in the hallway or something, but because of the random nature of picking a port, it doesn't always start at your starting port range. It's a random number in between there. So you loop through all of those, and then it kind of wraps around, loops through the rest of the even. Then we parity switch. Same again for the odd, and keep going in a circle such as that. So it could have the potential to miss certain cases. We can also pick a random port in user space and perform the bind before connect again. So this one's a little interesting. So with this approach, we don't have any direct metrics on it, but the idea is you reach a conflict with picking a random port, and then you just try it again. And you just do that over and over and over again. Now we find that this can introduce more syscall overhead because you keep having to make these connections, and it's good to about 70 to 80% of the port range utilization. But the problem is if you're already reaching this point, maybe consider something else. But it is a viable, I mean, it is a feasible option, but it also doesn't quite work for us either. Now the interesting thing is with the local port range socket option is that because we're now in control of the window ourselves per socket, this can introduce an interesting side effect in user space. And we can see here that even though we have 5,000K port window, we're making a trade-off saying that, you know, maybe we're not reaching our full 56,000, but you know, in this case, we're okay with 5K windows. We can exhaust that within about 1.5 seconds. The loop problems still persist. And it's evidenced by this bimodal here as well. But we found that if you kind of reduce this down to a 1K window size, we can reduce that to 2.2 milliseconds. And we can see here that the bimodal distribution is almost non-existent. So you would figure with smaller n, you would be able to go through your connections a lot faster. Now, another interesting idea with this approach is you can also leverage overlapping. So if you, and we'll go into this a little bit, but the idea is you can define different windows and you can kind of overlap them, and you just make the assumption that you're not going to exhaust all the ports within that all the time. So this is what we ended up doing. We added a random offset to our window. So we went from 3 minutes down to 9 seconds for exhausting all of our ports. And this is about 56,000 connections. And we're able to achieve about a 60,000 connection, or no, not 60, 6,000 connections per second with this approach. So let's take a look at how that works. So we start off with our system range of 9024 to 65535. And then what we did is we created some arbitrary range. In this case, is just 0 to 1,000. We take that range and then we subtract it from the high range. So what we're trying to do here is we're trying to still leverage our full system window, but we're only using 1,000 port windows at a time. And then eventually we go ahead and set that socket option, and this will just place a window randomly within our port range. But it's not, it's just good for visualization, but in reality, we're actually shifting the whole window around constantly per connection. We think overlap is okay. Reattempts may be necessary. We will get into that in a little bit, but in practice, this actually works quite well, and we can kind of see that. Well, I guess we'll get there in a minute, but using this 1K window, we're able to achieve very good performance, and this completely leverages just randomly placing this window wherever we want. And of course, we assume overlapping is okay. Now, there is something interesting about this chart that we didn't really see before. We've now introduced black dots. Black dots are connection errors. And we can kind of see here that once we reach the very end of our port range, then we're starting to get our conflicts with our connections. And that's where reattempts may be necessary. Or not, it just depends on your use case. In our case, we want to fail fast, very fast, so we can move those connections along. So we did some experimentation with other windows. In the 500 window case, we can see that we brought this down to about roughly 9.6 seconds. The error rate between 500 and 1,000 window is pretty comparable. All the stats here are very comparable between these two. But when we actually look at the 5K window or a 10K window, our error rate just dramatically increases, our time dramatically increases as we exhaust our port range. And this is due to the fact that the overlapping is now able to have more conflicts because our windows are so large, we're able to guarantee a port each time we loop through them basically. And well, now we get connection errors once we fill that all up. But also time increases. So now we're not at 9 seconds, we're at 13 seconds or 25 seconds. So this kind of kind of defeats the purpose of what we're trying to look for. Still a lot better than 3 minutes, don't get me wrong, but we could do better with smaller windows. So some takeaways: the current implementation always guarantees that a port is selected. It's also not great at extreme egress workloads, and we can reduce and then also with this socket option, we can reduce the port range to small loops. A nice little side effect of this is now you can partition, or you can partition IP addresses to your services. Just give them a specific IP port range, and then there you go. And then with the random offset or a 500 to 100 window coupled with the random port picking, it works pretty well. And the nice thing and the icing on the cake is purely user space implementation. But before we really get to discussion and questions, we kind of want to open this up to a form of discussing policy within the kernel. I've just explained a really unique case. Most cases don't need to exhaust the entire port range, but we need to account for that in our cache service. But the question is, what about other people? So not all the time user space is going to be able to provide the solution. So is there a way in which we can expand policy for picking ports? I know that the specification calls for various algorithms that we can use to pick ports, but right now we're kind of bound to this. We're always selecting every other port, looping, yada, yada, yada. So, all right, yeah, that's all I had to say. Thank you.
Yeah, I wonder, not for TCP, I wonder you have similar problem for the UDP. I know UDP has a connect, it's not a real connect, but they still allow connect. Have you looked at the efficiency of the connect in UDP?
Right. No, we didn't really look at UDP right now at this moment. I know I meant to mention this earlier that you know this whole thing can go out the window with UDP, for instance. But no, we only focused on TCP. Yeah.
Yeah, it'd be great if the same algorithm can also work on UDP.
Right.
But
Yeah.
It should be similar, I think.
Interesting. Well, try it out.
Okay.
So you probably like discussed it. So this randomization offset, why it doesn't randomize odd versus even?
I'm sorry. Why doesn't it randomize what?
With this offset, with the random offset that it starts, why it doesn't randomize whether it starts odd or even? Like it sounds like the algorithm always starts whatever even and then switches to odd.
Yeah, but that's yeah. So the algorithm does start that. There is randomization baked into it. Again, I didn't give the slides for that, but when we look at the offset calculation, that by default is randomized. It's mainly there for a way to prevent fingerprinting.
Yeah. This part I know, but like just did you try like adding randomizing the odd evenness? Like do randomly pick whether you go through odd first and then even.
Yeah, I mean that's what we're
Then
doing
this
with
whole-
the random offset. Is we start at a random. We could potentially start at a random odd port, do all the odds first, then the evens, or we can start an even, do all the evens, then the
Oh,
odds.
that's already there.
Yeah, with the random offset of the window.
Oh, so you mean are you saying the fix that you're providing is extra patch, or this is existing how it works? Because if it is, it kind of doesn't match the slides where you have like all the odd first and then even. Or I mean,
Right. No, that's exactly the point. Maybe I didn't clarify this earlier, but yeah, with the implementation as it stands, if you have a low, if you have your IP port window, if that starts the low end at an even number, it always loops through the evens first, then the odds. If it starts as an odd number, then it loops through all the odds, then the evens.
Right. So in my question, just add this randomization, and then you won't have this bimodal stuff.
Right, and that's what we're doing. Yeah, we're randomizing that. Oh, right. No, that's the discussion I'd like to have. Like, what can we do to you know to allow the kernel to allow different algorithms for port picking? What can we do to add some functionality in there to be able to achieve that? I don't have an answer for that, but
you mentioned earlier that there are also other heuristics, just that they haven't been implemented. I mean, outside from the random picking, did you also look into other things which like could be useful for workloads or?
Yeah. I mean, we explored various architectural changes, but with architectural changes comes with a lot of bureaucracy, money, time, things like that. So I mean, there's a few other things that we can try to architecturally speaking, or from the user space in this case. Like I said, this is a very trimmed down use case that we've only really looked at.
More questions? All right, thank you.
All right, thanks.
Yeah.
So good afternoon, everyone. Can you hear me? Okay, perfect. So this talk is all about the container networking. I know most of the guys are already aware about the containers and then its networking part, but here we will talk about the evolution of the container networking happened at Meta. So I'm myself Takshak. I'm part of the container development team at Meta. And the different type of workloads are the key elements which drives the container networking aspects of the configurations or the requirement. And we always partner with the kernel team to ensure that the latency, the throughput, and everything, whatever is required from the kernel side is getting taken care by for the specific requirements. So this presentation is a joint effort between the container and then kernel team. And Martin is my partner who is also here. We'll be talking about some of the aspects of the network namespaces and the different virtual devices. What we wanted to basically cover here is that there are different aspects about the networking. Do we really need isolation? At what level we need isolation? So we will talk about the L3 level networking isolation, which is plainly based on the Segro BPF. We will talk about, of course, the network namespaces and how the eBPF has helped us. Just basically building the solution without network namespaces, because we definitely need to see whether do we really need a network namespace to do something. I know most of the guys are aware that the container is powered by the different type of isolations provided by the network namespaces, and of course the bucket is basically accounted, and then resource has been channelized correctly with the C groups. But this basically has different variations when we talk about what type of container shapes we are having. Is it like a square shapes? Is it like a different type of shapes, like CPU is different, memory is different, the NIC speed or the bandwidth what we need is different, and every variation varies, and then the complexity increases that how we are going to stack the containers on a specific host. The different aspect here is could be like a single tenant host or the multi-tenant host. If it is like a single tenant, okay, however you want to stack it, you can go ahead and stack it. But when it is a multi-tenant, then definitely the isolation is the key. And we always need to think that, okay, what are the resources we are sharing? What are the resources we wanted to really have the isolation to, right? So let's take the plain look at this one where we have a single host with multiple containers. And this containers has been isolated with like PID and other namespaces, but no network namespace here. So what are the basically challenges we could see? Like every container just wanted to communicate with the outside world. And then as part of that, we can use the existing physical host space and network configuration and then just send the packet outside, right? So the moment we basically see that, okay, containers can do that, they don't need any additional configuration. But the moment we see, okay, a particular container wants to bind on a specific port to build a server at 443, and then now the container 2 also wants to basically do the same thing. Of course, it will not work because they are sharing the same host space, right? So these are the challenges. Now we could basically see, hey, if there is no isolation, there could be a problems in port management. There could be basically challenges in exposing the port to the different container or to the host network space. To avoid that, we need to see what kind of isolation we need to bring it. There could be another aspect that the service traffic is the key point here. Now the multiple containers are hosted on a single host, and they are basically sending traffic outside. Now, if you want to apply the different policies to different containers, that container 1 has like a gold policy for the priority perspective. The container 2 could be basically having like a bronze or silver policies. Now, if you want to identify this, that which container is basically sending traffic, and if you want to basically debug this from the outside world, definitely the eBPF could be the best solution. And we have this in the fleet where the eBPF-based policies are there, and which identifies that which container is sending what traffic. But when the host is basically not shared, whether it's like a single tenant, then you know that this host belongs to whom, and then what kind of policies we need to apply. But the moment we basically see that, no, this host has been shared with multi-tenants, then one is to identify that which container is sending a traffic. And then it becomes a challenge that how to debug to a specific container. And to identify that, now here is the thing that we need to give a network identifier to each of the container. Somehow we need to isolate that particular specific container is different than the host. And this is where we basically talk about having a unique IPv6 given to a container. Then the question comes that, hey, how we want to basically tie up the different IPv6 identity to the container. And here is the eBPF, which basically helps us that the cgroup BPF based bind, connect, and send message are the basic hooks which could help us to attach the identity, unique identity to the container. We basically did it in a very, very simple way that every container has a cgroup, and the cgroup program could be attached. I was just basically showing this the structure here. So whenever there is a bind happens, we have already predefined and pre-allocated the container IP, and then we just need to make sure that when the bind is happening, bind happens to the container IP rather than the host IP. And in this way, if we basically just override the user IPv6 here, the bind will go to the specific IP. And if the multiple containers wants to bind to the same port, now we can see that the container IP1, 443, and then container IP2, 443, and they can still coexist in the same network namespace. So we have not done any isolation here, but the cgroup BPFs are just basically helping it here. Similarly, when we want to do the connect, right, the source identity of the packet has to be defined correctly, and that is where the other cgroup BPF program helps here as a connect 6. And code snippet here is like two important things. What we need to do is, of course, rewrite the source identity as the container IP, and make sure that the outgoing traffic has that identity. So these are the basic ways to solve the problem. But is that enough? So that could be the question. So if you look at it, right, like the two containers cannot start the service on the same fixed port, and we have seen that cgroup BPF is helping at certain extent, right? But consider the case that we have the host, and on the host there are multiple other services running. If a particular host service is running on a wildcard, of course, no matter what identity we wanted to give it to a container, the container cannot basically do the bind. So there is like a loophole, or there is a limitations about the cgroup BPF, and then it doesn't solve all the challenges, right? The other way to look at it, like if I want to say that, hey, the container wants to listen on a local host, 9200, maybe like Elasticsearch service or maybe some Redis service. And the moment we assign the routable IP to a container and start the bind, it means that it is very much available to inside the host as well as around the fleet of the meta. And if you want to basically restrict it, giving a plain isolated environment to the container, then it becomes a challenge. Of course, cgroup BPF again helps here. We can have the peer cgroup checks. We can attach a program, but again, it's an overhead for us to manage it. Another challenges could be like a container could have multiple IPs. It's not only the container IP, the unique identity what we basically provide, but could be a BGP VIP, will be IPv4, IPv6, whatnot. And to do the wildcard binding, again, it fails. So cgroup BPF has that limitations, and then that is where we basically thought, okay, there should be some other way to solve the problem. And this is how the container networking has been evolved in the meta over the years, and now it has reached to a different level. There is another interesting problem I just wanted to basically iterate here is that we do a lot of the TLS. So whatever the traffic goes from one host to other host, or even from the origin to the outside world, is all TLS based. And this basically we do it without modifying the application logic using the cgroup BPF hooks. So whenever there is a connect, basically that get intercepted using the cgroup BPF connect hook, and we redirect to the local proxy. That proxy makes sure that actually it established the TLS handshake with the reverse proxy on the other host, or maybe to the forward proxy of the meta, and then the packet basically goes out. So all those things has been very well managed using the cgroup BPF. But the moment we talk about the UDP traffic, this again fails. So the cgroup BPF has its own limitations, and that is where we basically thought, now it's time to basically look into the different aspect, how we can evolve this networking. Another interesting thing, as you have seen, that Meta is basically heavily investing into the reliability labs, Horizon, and other projects, right? There are third-party components we run, the third-party games we basically run, and that is the reason we spin out the VMs inside the container, and then it requires different configurations. Like, for example, if you could see it here, we have the tab device created for the VM, and now the tab device is basically sitting on the host space. If we basically go for the multi-tenant host and then the stacking workload, then of course the multiple devices will basically just mess up the host-related environment. So, another additional use case what we have here is that we have the multi-NIC host as the Meta is getting for the AI infrastructure, right? We have the bigger machines which has multiple interfaces, and each container could basically have like 4 GPU, 8 GPUs, and based on that, there could be multiple NIC associated to a container. And to do this, basically configuration, making sure that the bandwidth has been utilized correctly among the multiple associated NICs, we need to basically set up a lot of ECMP routes on the host, as well as for the egress path, as well as the routes at the TOR level to do the ingress bandwidth management. And all those things, when we basically think, okay, C group BPF, whatever we had earlier is not enough, and that is where the reason is to basically move on to the different aspects. And as I said, that of course the use cases, whatever we have seen, we definitely need L2 level secure isolations. We also have the XDP based load balancers, so we need per container TC or XDP stuff, which definitely need a link device rather than choking the single physical ETH0 whatever way we used to do it. As I said, that we wanted to basically test a lot of Reality Labs devices. We need emulators and a lot of configuration related to it. So all those things definitely needs a different configuration, and that is where this is where basically we are like building the solution with the network namespaces. So we always thought that network namespaces is basically going to add an overhead. If you basically look at it, okay, how do we connect it, right? If it is a separate network namespace, there is a need of connectivity. The moment we talk about the connectivity, of course, we talk about the VETH, and then we have the double stack traversal problems. And of course, shout out to Daniel, who basically created a patch set, which basically helped us to move these redirections between the physical host to the VETH, and then we basically follow the same thing what has been upstreamed. And we implemented this. Another challenges we basically saw it here, that the global IP forwarding enablement, we used to do it on every host. Turning every host as a router is a challenge in our fleet, and that's where this BPF redirect has definitely helped us. I just wanted to basically add one interesting use case here, where we talked about the UDP traffic redirections, right? Using the C group BPF, it was not possible. Then we thought, okay, using the TC BPF, it is very easy, because we need to ensure that the tuple, the phi tuple, is basically is currently cached correctly. The challenge here is that actually when the packet, it's very easy to basically put the ingress and egress eBPF program inside the container. If you could see that there are the two Bs, and the packet can basically go to the egress. Before egress happens, we can reset the packet destinations and then put it into the locally running forward proxy. But when we basically try to do that, we have seen that the packet makes the round trip. It basically goes from egress path to the host end of the VETH, and then comes back as an ingress. And the moment basically it happens, the ingress program doesn't get hit, and it basically goes to the loopback. So Martin has basically provided a solution here, is that we attach the ingress programs to the loopback interface itself, and then instead of allowing him to go out from the task to the host side, we do the BPF redirect directly to the loopback, and that has helped us to avoid that traversal. So some of these challenges has been there, and yeah, so we validate the EV, but there are other ways to manage the performance in a better way. So I would like to give it to Martin to talk about those.
So I think Tasha talked about the reason we are
starting using more level namespaces. So we started to evaluate performance of different virtual devices, because one of the big complaint I heard when we start moving tasks to level namespace is performance, so using more CPU. Another one is suddenly use a lot more soft IRQ. I was told by multiple people that it is bad for C group CPU accounting. So let's see what we have tried. So we tried a few. So IPVLAN, we picked that because when I look at the code, it's super simple, very straightforward in the L2 mode. So that should be pretty fast. So WIF is the one that we are using, which people complain about the performance. NetKit, so is the latest one developed by Daniel Bobman. So we have tried that. Bare metal is like no network namespace, just send it out to the EF0. So if you look at the graph, is everything get Can you hear us? Okay. Okay, so so here we zoom into the graph that the previous slide. And so we zoom into the left part. So on the first bar on your left, so you start using the width, and then on the second bar, the vertical bar. Then starting from the second vertical bar, you will we start using NetKit. So you can see the CPU utilization difference start to close to the IPVLAN. So the NetKit is faster. So we dive in. So here we're still in the same comparison, comparing the width and the NetKit, but we zoom in. We don't look at all the CPU utilization. We only look at the CPU system time and the CPU soft IRQ time. So that is a need to more obvious on the differences. So now we focus on the soft IRQ usage on CPU. So moving from width to NetKit, you can see NetKit is using about the same soft IRQ time when comparing with IPVLAN. So on that side is a big plus on NetKit. But if you look at the system time, you can see the NetKit is using more system time, but that makes sense, right? Because you're sending out, you send out from the virtual device to the physical net, you need to use the CPU cycle, just where you are counting it, right? So it's a big high-level conceptual picture trying to explain. The red part is the time. So the SKP is sending out away from top to the bottom when you call send message. if the TCP allow you to send it out, it's not bounded by the send congestion window, so you should be able to reach all the way to the leg, send it out, right? So for width is, the problem for width is when you reach out to the width pair on the hook side, you will be in the backlog queue and then processed by the soft IRQ asynchronously. That's why some of the time, CPU time that you need to send out the packet get accounted to the soft IRQ CPU time. So as you can see in the previous slide, the lag kit and IPVLAN still have some CPU utilization difference, right? So lag kit is still a little bit behind in terms of CPU usage. So I look at the code. I did look at the code to compare what may be the difference. So in the kernel side, it should be pretty similar. Both of them should be pretty efficient. So I dive in a little bit to see what we are doing in the BPF program. So end up we are not. So we are comparing IPVLAN in L2 mode. We end up when I look at the BPF program, we are mostly operating in the L3 mode. So for every packet we are sending out, we end up doing a row lookup. So that is the one killing the performance here. What I did is I optimized the BPF program a little bit more to avoid the flip lookup to make it work more like L2 mode. So change the MAC header and then send it out to the lake. So that closed the gap a little bit more. So this focusing on the system, CPU system time and soft IRQ time, because that is easy to see the differences. So it's pretty close to the IPVLAN at this point. So I look at the, so what happened is the remaining differences here is the machine I pick have some background differences. So one of the machine has a different NIC. I don't know, that may be the reason, but what I did is I also make both set of machine one IPVLAN, and they have this similar amount of differences. So so it's comfortable that it's good, pretty good, the lag kit. So for this amount of this level of granularity of difference, so I go back to Michael benchmark. So what I did is do a TCP request and response test, which is a 36 threads test, sending 1 byte request and 1 byte response, which is pretty close to our usage. So I forgot to mention the graph that I just showed is a key value store. It's our production key value store. So it's the request and response is also in a few hundred byte sort of thing. So it's pretty close to the Michael benchmark here. If you look at the CPU utilization, is IPVLAN and Matter is still lagging a little bit compared with the bare metal, but it's definitely better than with. Yeah. That's all. Do you guys have questions?
Thanks a lot. So maybe can you go back to the results slide, the final one?
The last one, yeah.
Yeah. So I do not fully understand all the background here, but I'm just wondering why there's so little difference in the last 2 rows between the different approaches. I was expecting a lot more, transactions,
You
for
mean the
example.
last 2 rows, the row 6 and 7?
Yes.
Right.
6 and 7, right?
Yeah, for the width, it can do about the same amount of transaction, right? Because it still have just use more CPU, right? If you look at the second row. If you look at the width, it can do about the same amount of transaction per second, but you just use more CPU.
Okay. Okay. So maybe so it's probably that you are not even in an overload situation here. So that's what I would expect if you have a very, very high amount of traffic, that at some point the VEs will just, due to the higher CPU utilization, will just have does not allow more traffic than the other ones.
Right. Yeah, but usually we won't run into like 100% of the machine, right? Because
yeah.
we don't
okay,
want to.
Yeah.
Because everything is not the expectation of everything. We don't run the machine to 100%, but is this benchmark sort of like showing how much CPU it is using for the width? Although it's so here like it's like 1% or 1.2%, but that is a lot to us.
Yeah. Okay.
Right.
Thanks a lot.
Yeah.
Did you manage to compare maybe flame graphs between the bare metal and then the IPVLAN or Netkit in terms of this minor difference that is still there? Like what could be done to optimize it, for example?
Yeah, that's a good question. I didn't grab this frame graph, but from the code, I really don't see much difference. I suspect it's the sum of the indirect call we are doing. Let's say for the lag kit, we call the BPF program, you say indirect call, right? So those will be the things that I would look at if we want to improve it. Yeah. Another one is like, even we are working in the L2 mode, right? We want to redirect to the EF0. I'm seeing in the frame graph like we make the BPF redirect call. We need to pass the index, and then in the frame graph, it's observable. We're seeing making a kernel call def get device RCU. I'm seeing this, so maybe that's something we can optimize there also.
All right. Thank you.
Thank you.
Okay. Good afternoon, ladies and gentlemen. My name is Pavel Djibovitsky. I'm production engineer with Meta, and here with me.
I'm Roman. I'm working for containers team at Meta.
And I'm Lalit, and I work on the layer 4 load balancing team at Meta.
Today, we are going to tell you an exciting story of layer 4 load balancing and direct server return evolution at Meta. These network components evolved over the years, shaping the way we distribute traffic and ensure reliability of Meta digital services. Briefly, we'll talk about layer 4 load balancers and improvement in their implementation, challenges of heavily stacked containerized environment. We'll be focusing on direct server response and key takeaways on the evolution path. And hopefully we'll have some time for questions and answers too. The layer 4 load balancers distribute traffic among backends, making the decision based on the transport header, provide high availability, scalability, and what is important, session persistence. Direct server return is one of this method that is widely used in this world. In this case, the server bypass the load balancer on the way back, responding directly to the client. It greatly boosts performance of the load balancer, especially in the web app environment when the response could be larger than the request itself. On the way to the server, the packets are encapsulated, wrapped. It means that we need to provide something to unwrap them on the server side. Our original implementation was based on IPVS, which is widely used in Linux world, but it comes with a set of disadvantages. First of all, it's a CPU heavy. It was hard to collocate anything with a layer 4 load balancer. Another problem was it's too generic, and it has to maintain connection tables. Connection tables resulted in a bad performance when a large number of new connections is established, like during DDoS attacks. And finally, it was a part of the Linux kernel. In order to deploy new features, we need to deploy a new kernel version. We need something to move faster. When BPF XDP technology emerged, a decision was made to re-implement the load balancer using this groundbreaking technology. The XDP ability to run before expensive memory allocation is done proved to be super CPU efficient. Based on our tests, we were able to handle 3 times more traffic, consuming 7 times less CPU. Now we are able to collocate other services with a layer 4 load balancer. Also, this load balancer became stateless, so DDoS attack was no longer a problem. And finally, BPF program release was isolated from the kernel release. We were able to push new features daily. Katran project was a great success. It was open sourced, it's available on GitHub, and now on, we love with XDP. But what are the challenges of using XDP in production environment? Roman?
Thank you. Yeah, so we discovered a couple of challenges with XDP in production. One of them was the fact that there are multiple teams who want to attach different XDP programs on the host. Some examples are like firewalls that run on the host level or load balancing XDP programs. And those programs can be attached at different times and dynamically, and they still should have some expected order of execution. And so to address these issues, internally, we built XDP chainer. So this program was using BPF dynamic extension program feature, and it published 20 different slots for other programs to attach. And it was sitting as an XDP program on the network device itself. For this program also guarantee that all slots are executed sequentially in the same order. And each program can reserve, or each team or the service can reserve the slot in advance in a static configuration. And also on the host, our container orchestration system makes sure that this XDP chainer is only attached to network device when there is at least one slot is occupied. So on this diagram, you can see the kernel space and user space view for the XDP chainer. So in the kernel space, it's just go over the available slots sequentially, and each of the slot can return the actual response, like XDP drop, pass, or redirect, which will be honored. And on the user space, containers can actually load, set priority, and attach programs to a specific slot that they reserved in advance. So with XDP decapsulation implementation, we saw some minor performance gains, like about 5% soft IRQ CPU. It was also a simplified setup to attach XDP program to the XDP chainer on the host. And with XDP implementation, we also gained statistics published from the kernel space by BPF program. And the following diagram show the logic around XDP decapsulation solution. So you can see that encapsulated packet went on a physical device, network device, and it has XDP chainer. And one of the slots on this XDP chainer is allocated by XDP decapsulation program. So once this program decapsulates the packet, the host then route this packet to the correct container on the host, which serves this specific DSR VIP. And although we liked the XDP approach, we also discovered a couple issues, in particular security issue. The container itself needs elevated root access, so it can load and attach this XDP BPF program. And also there is an issue with release cycle for XDP chainer itself. To update the XDP chainer, we need to make sure that all slots are empty, and basically the host should be drained for to get the new version of XDP chainer. And also we faced some additional challenges with DSR decapsulation done on XDP level. So if we have two containers stacked on the same host that serve the same DSR VIP, we will have issues and need additional work to actually route this packet to the right container on the host. And yeah, back to Paul.
Yes, stacking multiple services on the same machine, making our infrastructure super efficient. But in absence of the network isolation, it comes at a cost of cross impact. There are a few categories of the cross impact. One is related to traffic black holes. Imagine that there is an application that was serving a VIP. On shutdown, did not remove it. Something went wrong. This VIP would still attract host traffic, but nothing would serve it. It would be a traffic black hole. A similar problem can be caused by the routing table manipulation. Another problem is related to security and accidental exposure to the internet. One service can be opened, has a VIP that opens through the firewall, and another on the same machine, if it listens to wildcard, it could be accidentally exposed to. It's a security risk. And finally, there is a performance impact. One service can open large number of sockets, especially UDP sockets, and other services on the same host would suffer trying to find a source port for outgoing connection. It is why we love networking spaces that provide us an isolation of the system resources related to networking. It's each container gets its own IPv4, IPv6 stack, routing tables, set of network interfaces, including loopback. It allows multiple services to serve the same VIP without stepping on each other. It allows us to configure firewall on the container level with rules more precise that could be configured on the host level. And finally, it resolves most of the cross-impact issues. But how can we plug them in our infrastructure? Our initial approach was to reuse XDP decapsulation. In this case, the packet would come to the host, decapsulated with a XDP program, and then would be redirected to the namespace that is serving VIP. But it comes with some disadvantages. One that Arman mentioned, if two containers serve the same VIP, we have routing ambiguity. Another problem that in order to forward, redirect the packets, the orchestration system needs to be aware of the VIPs that are served in each container. And it did not allow us to create VIPs dynamically after container is started. We needed something else. The solution came from the fact that actually each of the network namespaces has its own IP address. And this IP address can be known to the layer 4 load balancer. So the layer 4 load balancer can use it in the outer packet as a destination IP. What if we would allow the packets to enter the namespace, delay and decapsulation, and unwrap them in the network namespace itself? How would we do it? So since performance gain from the XDP decapsulation was minimal, we decided, okay, let's go back to the kernel modules. We implemented our pilot, and we realized that we have actually 8 to 10% latency increase for the services. What did we miss? In order to improve traceability, at some moment, we migrated from IP and IP to generic UDP encapsulation. And now, instead of IP tunneling, we have like a full over UDP kernel model responsible for decapsulation. But FOIA would not complete the decap. It would just strip UDP header and re-inject packet into the stack. Then there would be a tunneling driver to take care of the outer header, remove it, and re-inject packet into the stack. And this multiple travel through the stack resulted in increased latency on production load. It was good for the pilot, but we need something better. Walid.
Thank you, Pavel. Now, to solve the latency issue of the full tunnel-based decapsulation approach, we needed a way to decapsulate the packet in a single pass, like the way we were doing in the XTP-based decapsulation approach. And to do that, we wrote a custom TC-BPF Decap program, which we attach at the V device of the container running in a network namespace. And when an encapsulated packet comes on the host, then it gets routed to the container whose IP matches with the destination IP of the encapsulated packet. And when this encapsulated packet reaches the V device of the container, it gets decapsulated by this TC Decap program before moving up in the networking stack. We have this TC Decap solution fully integrated in the container orchestration framework. And by having this solution provided through container orchestration framework, services which needs the solution can directly request it through container spec. And by having this solution provided through container orchestration framework, we can also remove some of the elevated privileges which was previously required to attach XTP-based decap solution. And this improves the overall security of the host. And during our early pilot testing of this TC decap solution, we found the latency issue that we saw in the full tunnel-based decap approach to went away in the TC decap approach. And this is a great win for this TC decap solution. We benchmarked this TC decap solution against XTP-based decap approach, and we found the runtime of this TC decap to be very close to the XTP-based approach. In fact, the TC decap's program was only around 6 nanoseconds slower, which is completely acceptable. Moreover, this TC decap solution provides the same decap statistics that we had in the XTP-based decap solution. And so in summary, this TC decap solution provides all the benefit that we had in the XTP-based solution, but it's at the same time, it also solves some of the issue that we had in the TC decap approach. With the help of network namespaces, we set up an isolated end-to-end test to test this TC decap solution. And more specifically, what we did is we set up a client in the outer, we set up our 2 network namespaces nested within each other, and we set up a client in the outer network namespace and server in the inner network namespace. And we attached the TC encap program on the VEAT device of the client namespace and the TC decap program on the VEAT device of the server namespace. And when the client sends a packet to the server, it gets encapped by the TC NCAP program at the wheat device of the client namespace with the destination IP of the namespace of the server. And when this encapsulated packet reaches the wheat device of the server namespace, it gets decapped by this TC decap program before reaching the server. And when the server receives the packet, it responds to the client that it has received the packet. Since this TC decap program is attached at the wheat device of the network namespace, we initially thought that this would catch all the bugs. However, hardware matters, and we found out that different behavior exposed by different vendor can affect the working of the TC decap program. And during our early testing of this TC decap solution, we found two issues that was occurring on host running specific network device. For example, one issue we found was occurring on the host running Mellanox device. And in short, the issue was Mellanox by default enable complete checksum. And when this TC decap program was trying to shrink the SK buff in order to remove the encapsulated part, then instead of computing the checksum from scratch, we just subtract the checksum of the encapsulated part from the total checksum. However, due to a bug in the TC BPF program, the encap header was modified just before the shrinking of the SK buff, which led to the incorrect checksum. And the second issue we found on the host where Broadcom device was running, and there the issue was SK buff didn't contain any bytes after the UDP header. However, we needed the first byte in the UDP header to be able to figure out what kind of encapsulated is done for this packet. The bottom line is that these kinds of issues are hard to mimic in testing, and some bug would manifest on specific hardware only. One way to catch those bugs would be to set up some kind of a synthetic end-to-end test where we have backends running different kind of network devices. Lastly, in the direct server return path of server running in a network namespace enabled server, we have slightly increased CPU utilization due to the increased Soft IRQ in the wheat device. This is a well-known issue and has been addressed by Daniel at iSolvent with the NetKit device. We have tested this solution at our Meta infra, and we found the result to be promising. And we will be implementing the solution so soon to resolve this issue. In closing, I want to say that this eBPF technology have been extremely helpful in the evolution of layer 4 load balancing and DSR technology at Meta. Whenever we faced any issue, there was an eBPF solution that was available for us. Thank you very much.
So I think it's great that you talked about different hardware platforms you tested on. That's cool. We don't see that a ton, so that's good. One of the things I was curious about is lots of hardware can maybe not do automatic decap, but can do packet split, and will actually put all of the Geneve headers, for example, should put it in the header and should put the data as only in data. Did you investigate whether or not it would be possible to have the hardware? It doesn't solve one of your problems, but to have the hardware essentially split the packet for you after it was in-capped at the load balancer and skip that part of the BPF program. And it's okay if you didn't. I was just curious. It'd be interesting to think about. It would save you one program from running.
I think this is an interesting thing. We haven't investigated that.
Yeah, okay. Be happy to help.
So you mentioned that you still have a performance gap of like 6% between XDP and TC. What's the difference?
Not 6%. The runtime was 6 nanoseconds. The TC BPF program was 6 nanoseconds slower than the XTP based.
Okay, but do you understand why? It's presumably you're doing the same decap at different points.
I think the reason may be that this TC decap solution, TC BPF program operates on a SK buff, which is a much larger data structure, whereas this XTP program operates on a much smaller data structure. So maybe that could be the reason.
Yeah, I guess it's just weird that you're essentially still consuming the packet on the host.
Yeah, just a random guess here. I think it go back to earlier, like XDP. I think I remember XDP has some dispatcher to avoid the indirect call thing, but the DC BPF doesn't have it. It could be that 6 or 19 or something.
Or maybe TCX is what is actually they need to, right? Because you're probably still using TC actions and filters. And okay, thank you.
I wonder whether it would help users if, I don't know whether NetDev sim is the right place or so, but like somehow to emulate, to have like an emulation for the different behaviors around the checksumming, right?
But test prog, no? You can like run the test prog and then you can provide all the geometries that we can think of and they can provide what the results should be, and right? Did you guys look at the BPF test prog as a way to test your program versus various geometries of SKB and various conditions?
Not yet.
Yeah, on the checksum thing, it's easy. We exhaustively test every possible checksum because we've had the same kind of similar bugs before in silly cases with like 0 and full set.
So in the case for them was that they have checksum complete, right? So when they attach to the XDP, the driver knew that there might be something funny going with checksum, and it would disable checksum complete and go to checksum unnecessary.
Okay.
So the SKB metadata carries the checksum, and the BPF program needs to be careful to readjust that checksum with whatever it's doing with the packet. So when you move from the XDP to the TC, the driver no longer does the magic.
Yeah.
Yeah.
You mentioned with your XDP chainer that upgrades were hard because you had to like drain the whole server. Could you talk more about that?
Yeah, so XDP chainer, so we only can attach at this time only a single program to the network device. And so to actually update this program, we need to make sure that all attached programs in the slots, they detached in advance, just to avoid like any downtime for them, because like it's like separate services or separate teams attaching their programs.
Right? Oh, Martin, one more.
You have a question on your earlier slide. You mentioned there's a L port in use call is low. Is that about a UDP? Then go back to the earlier slide. You mentioned before you moving to the level M space, you have one thing that is low. This one, UDP lib L port in use. So you observe when you move to LNS, it help. Okay.
Yeah, before that, it was a strobe light trace when this function took us 50% of the CPU of the process, for instance. It's heavy.
All right. Stan, you want another one? Oh. All right. 30-minute break.
I know, but that's the best I can get. Yeah, it was good. It's good talk. Yeah.
Thank you.
All right, sorry.
We should allow if the user right the user
So how are you, what are you running? All right. Yeah. Okay, but just so you know, how is like, would they consider a good profile for binary is like around 200 million. Oh, sorry. I think it's really low. I know, but I think it should probably be that much more like, oh, wow. Oh, okay. That's like, for me, So what we can do, and we would gather LBR samples for the kernel, the whole thing. You wouldn't have to do it on the. My understanding. Good, good. Yeah. Well, when you say slow, you say do a profile. This whole process. Right, the one thing is that you samples already in the database, you don't have to do all
Oh, yeah, and shoot us out.
I know, this guy. So there is, yeah. I'm like, I don't want this. Because there's a lot of stuff that's not represented anymore.
Yeah, I mean, I can show you the question. Because I always look at But like, what confuses me is like that doesn't come into the sounds like
Yeah, so there was a different batch.
It was like a restore.
No, there was a
No, what I'm saying is like the new kernel build with the FCA.
I think we discussed it before somewhere. But again, it's maybe 4 lines.
You want me to sort of like build some plumbing for this process into our sales pipeline? And then you don't have to do it. You can just run this script. They have sort of like a CLPR. And run it. I mean, just it might make it easier for us, you know, to sort of manual stuff, but it's okay. So would this be going like that? Yeah. Pipeline? Next gen. Yeah, that's right, yeah. So when you want to use, yeah. All right.
So you just say you're just following along and we'll try to 56.
Oh, no, I would brought it down already. If what he said would work, right, like, you can build it, separately itself, like, if I wanna have it. Yeah. Well, because I needed to tell, teammates to go look for it. Wait, but we're not right for everything, or is it just? Wait, but wouldn't that override from all of it? Yeah. So, doesn't quite use that, but we maybe use something like different for that. Yeah, it's there. Yeah. And is it not using any headers from the style on one machine? Whatever. Would be that would go with? No, I'm on like the BPF next trip. So like, one meter, so we can. This one, this machine, oh. Right, right, so how would we go look at the different, the kernel headers that are built in different. How do I tell it to go? I would be kernel holder. Oh,
Do you want this again, or?
I would take it.
I put one of yours by the blue backpack. I'll just put this one here.
I'm probably stealing your seats. The anointed one can sit here.
How did it feel to sit in the seat? So it's like someone sitting in the king's throne of the kingdom there, right? So, yes, look up? Or that?
I don't really care.
I mean, configuring things to get up, setting something to get up is
Yeah.
like setup doesn't allow you to return.
Yeah, that's what I was mentioning. So the whole like set, yeah, like not that all, right? But
If you do get lookup, you can also you can both send data and receive data, but if you get to do send, which is
but you can abuse it.
yeah, Eric likes to use.
Well, and I think you brought up a great point, right? That maybe gets like up to do it to satisfy the BSD.
Yeah,
folks,
yeah.
so that it can be used in more places. But again, Netlink is implemented in FreeBSD in some.
Yeah, they do have network. Yeah, they have the original RT network. They want
I mean, either way, I want to know how to be able to do like that. I want to be able to see.
From the admin side?
Yeah.
Yeah, but it doesn't necessarily mean you program the keys.
Yeah. You don't have to program that. What? Well, yeah. So
this is not, you can put it in or hold it, it's up to you.
Yeah. Well, yeah,
oh, wait,
I think
so,
so I didn't talk about.
You lost Daniel? Oh, Daniel.
You can set each of them. This is what we're talking about. So you know, okay, these are the key signs. These are the different.
Oh, I guess. Oh,
yeah, I think that's probably that. I think Netlink in some ways is easier for Joe. Us, that it's like easier to convince people. That's what easier. But yeah. No one.
Audio is too. Okay, let's deal with that later.
Right. And I think, John's point is the most valid point. And that's the part that I was hoping by now. No, but that little part. That little part. That's not part of it. So, let's say, and then we have part of it. We have some project.
I'm gonna close the door.
I just don't like. You gotta get there.
Okay, let's get started. Hello, everyone. I'm QUIC, working for AWS. Today, I'm going to talk about our SYN Proxy implementation using kernel module. And the subtitle here is the question from the kernel module owner, and this drove me to combat it with BPF. Before talking about our SYN Proxy, I'll explain about QUIC implementation in Linux and what the problem is. Then I'll walk you through how our SYN Proxy works at scale. And finally, how we can use BPF to rewrite it. Basically, TCP connection establishment is stateful, and the server has to keep some state of the client. However, under DDoS attack like SYN flooding, it's painful to allocate some memory or CPU resources to the malicious connection request. So QUIC is used in such a situation not to allocate any resource for connection that does not complete through a handshake. The server encodes the client information into SYNAC, which is called QUIC, and they decode the same information from the ARQ. This way, the server need not keep any state for the malicious connection request. So the same encoded value in the SYNAC must be extracted from the ARQ. And the Linux kernel uses two stages for QUIC. And the first one is the initial sequence number, which is 4 bytes value. We can get the same number from the ARQ because the client acknowledges the ISN and the return ARQ, where the ISN plus 1 is the ARQ number. So we can decode the client information from the ARQ number minus 1. And the second stage is the timestamps option. TCP timestamps option include two timestamps, TS value and TS ECR, and both of them are 4 bytes. TS value is the timestamps of the sender of the packet, and the TS ECR is the last timestamps from the peer. So basically, the TS value in SYNAC is echoed back in TS ECR in ARQ packet. Okay, next, let's see what is encoded in the SYNAC. First, ISN is generated by this function following the old age formula. And 5 information is used to calculate ISN. First, for tuple is used to calculate 2 hashes, and client ISN is added to that ISN. And also MSS is included in the ISN. The data here is the MSS, but it's not actually the MSS. The data is an index of an array, MSS top, that has predefined MSS. So here we find an MSS from the array that is close to but less than the original client MSS. And the system timestamp is also encoded into ISN. The count here is the timestamp of the cookie, and it is calculated based on jiffys so that the timestamp increases every minute by 1. This value is checked when validating ARQ. And if the cookie is generated more than 2 minutes ago, then the connection will be aborted with reset. And finally, 2 secrets are used to calculate the ISN. The argument C is the index of the QUIC secret, which is used for SIP hash. And the secret is initialized only once for the first QUIC after boot up. And the same secrets will be used for the following QUICs. So ISN will be formatted like this, and it's summation of 3 32-bit values, and it includes 4-tuple client ISN, MSS, and a system timestamp, and a secret. When receiving ARQ for the sync cookie, the kernel calculates the salt hash from the ARQ and the ARQ number -1, and it checks if the timestamp and MSS index are valid or not. Next, we'll see what is encoded in the timestamps option. In timestamps option, the kernel uses only the lower 6 bits to encode the client information. So the value is initialized with the usual timestamp, and the lower 6 bits are cleared. And then, depending on which TCP functionality is available in the connection, and the corresponding value or flag is set to the lower bits. So the timestamps option will be formatted like this. And as you can see, this value has important information related to TCP performance, like window scaling, selective ARQ, and ECN. To summarize, the Linux kernel encodes this information into ISN and a TS value. And as the drawbacks of sync cookie, these 2 points are often mentioned. Precise MSS could be lost, and if the client does not support timestamps option, window scaling, selective ARQ, and ECN cannot be used in the connection. And there is one more drawback. That is, the sync cookie contains host-specific bits, like GFEs or random number. These values are different on each host. So let's say host A and host B are placed behind load balancer, and a sync cookie is generated by host A, and ARQ is misrouted to host B. Then only host A can validate the cookie, and host B cannot. So the ARQ is responded by reset from host B. So the sync cookie in Linux must be generated by the same, must be validated by the same generator. And this is for security, but it's actually a downside for in a point of view. So that is, so sync cookie is not stateless in network. With sync cookie, the server itself can remain stateless. However, the intermediate node between the server and the client still need to keep some state for connection. For example, firewall need to track the connection, and the load balancer need to remember portables. This is the problem of the sync cookie. Now let's go to the next section. And one of our services is capable of serving multiple terabytes per second in large regions. So there could be much more unwanted resource allocation by attacker. And ideally, only the validated packets should flow into our network. So to reduce unnecessary resource consumption in network, we needed scaling SYN protection that works at the edge of our network. And we have decided to use SYN Proxy. Basically, SYN Proxy handles the 3-way handshake instead of the backend server first. Then the server, the proxy uses sync cookie. And after 3-way handshake with the client, it initiates another 3-way handshake with the backend server using the decoded SYN packet. Before building SYN Proxy by ourselves, we have defined 3 tenets for SYN Proxy. The first one is to reduce the SYN fraud to manageable level. And the second one is never sacrifice connection quality. And the third one, this is the most important thing. The SYN Proxy must remain stateless for scalability. The Linux kernel provides out-of-the-box SYN Proxy features like NetFilter or BPF, but these features are all stateful. So we cannot use these features for our SYN Proxy. Because these features reuse the same SYN cookie infrastructure in Linux kernel. So the SYN cookie will have the host-specific bits, and the misloading scenario can be applied here as well. Let's say SYN Proxy node A generates SYN cookie, and its virtual IP is reassigned to SYN Proxy node B. Then ACK will be routed to the node B, but it cannot validate the cookie generated by the proxy node A. Then the connection will be aborted. And also, the conventional SYN Proxy must manage ISN mappings. So let's focus on the sequence number in two SYN ACK packets. In the first handshake, the sequence number is C, and which is generated by the SYN Proxy. And the SYN Proxy initiates another handshake after the three-way handshake with the client, and initiate another handshake with the actual server. And then the sequence number generated by the backend server is not C. So all the following packets have weird sequence number in the client's point of view. To be transparent, SYN Proxy must fix up the sequence number and ACK number in all of the following packets. So that means the SYN Proxy node must manage state for the connection. And if the proxy node is down, all the connections through the node are also terminated. So the conventional SYN Proxy is stateful and thus hard to replace and does not scale. To overcome these shortcomings, we use different cookie format and a kernel module at the backend server. And I will explain step by step. The first, what's encoded in our ISN. We use only ISN for SYN cookie storage and do not use timestamps option because some of our customers disable timestamps option for security reasons, like not to expose system time. And so we only use the ISN for SYN cookie. And the ISN includes the availability of selective ACK and window scaling. So we can keep connection quality without timestamps option. And MSS is also encoded in the same way with the Linux kernel. And the most important part is the hash. Hash is calculated with 4-tuple, client ISN, client TCP option, etc., and lowering salt. Lowering salt is a random number, which is updated periodically. And the lowering salt is shared by all the proxy nodes. So it means that any node can generate and validate SYN cookie statelessly. For example, if node A and node B generate SYN cookie for the same connection, then both values are the same one. Thus, both nodes can validate the cookie. So the misrouting scenario cannot be applied here. And after the three-way handshake, SYN Proxy forwards ACK within the decoded SYN packet, like TCP in TCP. So the forwarded SYN includes the ACK as the payload. And the following operation is delegated to the kernel module at the backend server. So SYN Proxy need not wait SYN ACK from the server, nor keep any state for the connection. And when SYN packet comes into the server, the kernel module hooks at net filter and extracts SYN packet from the TCP in TCP packet. Then it feeds the SYN packet to the TCP stack. Then the kernel generates SYN ACK. Of course, it has different ISN with the SYN cookie. So the module drops the SYN ACK, and it looks up the connection socket from the TCP hash tables and forcibly rewrites the ISN with the SYN cookie value. Then the original ACK extracted from the TCP in TCP packet can be used to complete three-way handshake. So here is a summary of how our stateless SYN Proxy works. The ISN does not expect it to be rewritten after initialization, however. So this is dirty hack, and it's basically unsafe, but now it's working fine. And however, Amazon Linux kernel team provides many versions of kernels for internal teams. So maintaining this kernel module is getting harder for the owner. And the countermeasures owner was looking for a way to maintain the functionality more easily. And that's where the team asked the first question, like, is it possible to rewrite ISN with BPF? And of course, it's no. And I was thinking how we can drop the dirty hack. And this is the basic idea. So if we could validate custom SYN cookie and create connection from it, we need not rewrite ISN unsafely. And moreover, SYN Proxy need not forward the decoded SYN packet, and we can simplify the flow. So I suggest adding a functionality to validate and ultimately act with BPF. And the first question would be where to invoke BPF program. ARC for the default SYN cookie is processed like the right diagram in the slide. When it's come to the TCP stack, first, listener is looked up for the packet, and later cookie v4 check or cookie v6 check validate the ARC and allocate the request SK and configure it based on the decoded data from the ARC. So the BPF program also need to access TCP header to validate the packet and configure request socket to set MSS and enable other some features. So the cookie v4 check or cookie v6 check was a natural point for me to hook BPF program, and actually I did in the version 1 patch set. However, Martin at Meta suggested to hook at earlier point. So when the packet comes in, we can validate the ARC at TC, and if it's valid, we can call kfunc, the allocate request socket, and configure it based on the argument and set the socket to SKB. Then in the socket lookup function, we can steal the listener from the request socket to enter the cookie v4 check. And in cookie v4 check, we can skip the validation if SKB has request socket. Then next, I'll explain how to use the kfunc and then how it works in details. So the BPF program will look like this. The program looks at TC when a packet comes into the host. And first, the BPF program checks if the packet is ARC, and it looks up socket based on the packet. And if the socket is a listening socket, the ARC could be for the SYN cookie. Then we can parse the packet and validate it. And if the packet has a valid cookie, and we can populate struct TCP cookie attribute, which will be used in kfunc to set up the request socket. Then finally, we can call kfunc to assign a new request socket to the SKB. The argument of the kfunc is SKB, a listening socket, and the dedicated struct and its size. And the struct TCP cookie attribute has 2 members. Most of the connection attribute can be expressed with available TCP options. So we can reuse the TCP option receive struct, but it does not have ECN attribute. So I added a Boolean value to express ECN availability. And this struct could be extended in the future for other attributes like TCP microsecond timestamp, which is added by Eric at Google. So then, an older program compiled with the old struct information definition could pass an initialized struct to the kfunc. So we need to check if the pass struct size is the same with the current definition. That's why this struct is packed. Otherwise, the Boolean value will be counted as 4 bytes, and we cannot detect the new member. And next, let's look at kfunc. It allocates a request socket, but it does not hold any left count of the listener. So, but request socket need to be tied to the listener so that later we can fetch it in the socket lookup function. So if we need to flee SKB, we need to create a listener before fleeing the request socket. Otherwise, the listening socket left count is wrongly decreased. So, and this socket can be differentiated with SYN cookie frag, which is currently not using the LX, the LC pass. So in the LC pass, if the SYN cookie frag is 1, it means the liquor socket is allocated by kfunc. And kfunc initialize a liquor socket based on the argument. However, here it is not pre-initialized. For example, the ISN will be set later in cookie v for check. And finally, kfunc set the request socket to SKB and also set SKB's destructor with sock p3. And in sock p3, as I mentioned before, we don't hold listeners left count here. So if SKB is split, we need to unlink the listener from the request socket. Otherwise, request K3 would accidentally decrement the listener's count. And later in the inet lookup SKB, we call the inet steal sock. And there we need to return a listener so that we can go through the SYN cookie validation function flow. So if request sockets SYN cookie frag is 1, we return its listener. The notable thing here is we do not clear SKB SK so that it can be carried to cookie v for check or cookie v6 check. And finally, in cookie v4 v6 check, if SKB has SK attached, it's the request SK allocated and partially configured by kfunc. So we complete initialization here and create a full SK later. And this way, we can validate an orbitally SYN cookie with BPF. So this is the last slide. To summarize this presentation, SYN cookie in Linux is stateful and thus not scalable. And also it sacrifices performance if timestamps option is not supported by client. But with BPF, you can create your own cookie. And so you can build stateless and scalable SYN proxy. That's all my presentation. Thank you for listening.
Questions, comments?
Have you had a chance to compare this BPF implementation to your kernel module in terms of like performance, QPS, and?
So we haven't actually compiled our BPF module, so I haven't measured the performance.
Okay, thanks.
What's the status of the second version? Is it merged upstream?
Yeah, so I wanted to post a V2 before this presentation, but there was some conflict in the net tree and BPF next. So, but now I think there is no conflict, so I can post the V2 this week.
All right, I just didn't see it, so I was wondering whether it's just me or it didn't come out yet. All right, no more questions? Thank you.
Yeah, thank you.
Yeah. Do you want to wait until the full hour, or do you want to stop?
So hello everyone. So I'm here to discuss about BP Filter, which is a BPF-based packet filtering framework. Okay, so I'm like, sorry. So I'm Quentin, I work at Meta. I'm in the Linux user space team. So we work on various open source projects. And I've been working on BP Filter for almost a year now. And so we're gonna discuss about packet filtering and globally firewall. First of all, what is BP Filter? Originally, it's a user model per in the kernel, so a kernel module that starts a user space process. It's been developed by Alexei, Daniel, and David Miller. And basically what it was doing is that it would catch the get socket and set socket code from iptables legacy into the kernel. It would read the content and create a BPF program out of it. I'm talking about iptables legacy because iptables and iptables legacy are slightly different. Iptable legacy is using the get socket and set socket call, while iptables is using the netlink protocol to communicate with the kernel. And the content inside the request is slightly different. So what BPF filter was aimed to do, as I said, was translate the filtering rules into BPF programs. At the time, so there is a kernel module right now called BPF filter, which doesn't do much except proving that it's possible to catch the get socket and set socket calls. There was a patch series, a V1 and V2 from Dmitry Banchikov a few years ago that would actually implement the packet, the BPF program generation. But that was just a patch series which has never been merged mainline. And the project has been kind of abandoned since 2021. And I've been taking it over earlier this year and moving into user space fully, so not in the kernel anymore. The structure of BPF filter in user space is composed of two parts, the library first and the daemon running in user space. The library is linked to the client, which could be iptables or nftables or basically anything you want to use. It's used to communicate with the daemon, so it's going to send the request from a client to the daemon with the format used in your client. If you use iptables, it's going to send the ipt replace structure, ipt entry stuff. If you use nftable, it's going to send the netlink messages to BPF filter. So it goes through a Unix domain socket where the daemon is listening on. And on the daemon, there are three major parts, which are the front end, the bytecode generation, and the program management. The front end is used to translate the data coming from the client into a generic format in BPF filter. The bytecode generation part, we'll talk a bit more about it later, but it's basically creating the BPF program from the rules sent to the daemon. And the final part is just to load the program and attach it to the kernel. So libbpf filter aims to be a very lightweight library, just used to transmit data across the Unix domain socket to the daemon. We can see a piece of code here, which is the proof of concept I've got for iptables. So I've modified iptables to use libbpf filter if you pass a --BPF flag. We can see it's very simple, and libbpf filter, which is called here on BF ipt replace call, is basically sending the iptable data to the daemon. There is no translation done at this point. It's just like the raw data sent directly to the daemon. And the whole leverage, like translation into a generic format and understanding what the rules contains, is done in the daemon itself. So it doesn't need much more work on iptable. So if we come back to iptable, so that's iptable's legacy still. The proof of concept, which is linked to libbpf filter, will send the ipt, what's called ipt replace structure, directly to the daemon, and it's going to be translated into a generic format, as I said, and converted it into a BPF program. The way iptable legacy works is that when it communicates with the kernel, it either request all the rule sets or send the whole rule set. So you can't just add one rule, you have to fetch the whole rule sets. And you can't just request one thing at once, you have to get it all. That's a downside of iptables, which could be fixed in BPF filter, because right now, if you change a rule, you regenerate the whole BPF programs. It might not be mandatory, it can be fixed, but it's not a technical issue, it's more like a time issue, which I don't have much right now, but it's not mandatory. So when you use iptables, we can see the dash, I don't know if you see, yeah, you can see. We can see the -i input, -pudp, and then an interface and an action. So basically what we are doing here is dropping every UDP packet coming in a specific interface. So when the request goes to the daemon, what happens is that from the time we have the generic format in BP Filter, it's going to go through all the rules, and we have one here, and it's going to unroll the rules and create the BPF bytecode that goes with it. For IP tables, it's using, when the program is ready, it's going to load the program to the kernel and attach it to the BPF net filter hooks, which are available since Linux 6.4, which ensure the program is attached to the same hooks as IP tables is filtering. That's quite new. And before that, I was using the TC hook, but the issue with TC is that there is no routing done at this point. So if you want to filter on input or forward, for example, if you receive the packet on TC, you don't know yet if the packet is targeted to your host or not. So I had to do a fib lookup at this point. And having the BPF net filter hooks is much better, I think. So IP tables provide a few things like counters, for example. So you can check with IP tables how many packets or bytes have been matched by your specific rule. And BP Filter also supports that using maps. You can filter on IP, on port, on protocol. But IP tables legacy is not much used anymore. What's used now is more NF table. The difference between IP tables and NF tables is that NF tables will use netlink to communicate with the kernel. So when you create rules with NF table, it's going to use netlink messages to send the rules to the kernel and receive data from the kernel. It doesn't, like IP tables, like fetch the whole rule set or send the whole rule set, but just the difference. And I've been working lately on supporting NF tables. I've discussed with Florian Westphal and Pablo also recently during the NetFilter days. Don't know the name, what the name is, I don't remember. But we've been discussing about BP Filter, and Florian was interested into using BP Filter to offload NF table rules on XDP. So I've been working on this prototype, which is a modified version of NF tables, roughly like it's done with IP tables. So there's a -b flag which will use libbp filter instead of netlink. And basically, instead of trying to modify the data structure or send something specific to BP Filter, we just use the netlink message, we send it to BP Filter, and all the leverage of understanding what the content of the message is and what the rules are, it's done in BP Filter. So this, at this point, is still, for BP Filter, a Unix domain socket, but the data is what you would send on a netlink socket. So the data is sent to the daemon, and the daemon use lib netlink to process and parse the netlink data and try to make sense of it, basically. Another big difference between IP tables and NF tables is that if you create a rule with NF tables, it's going to send the netfilter bytecode to the kernel, not some kind of structure containing the IP to filter or the port or the protocol, but basically just bytecodes. And this makes things a bit more complicated because we need to make sense of what the bytecode means, because it's quite similar to what BPF bytecode is at this point. And so with NF table, when you create a rule, because the purpose of it is to offload the filtering to XDP, an XDP program is created by BP Filter and attached to the kernel. Let's dive a bit more into bytecode generation. So basically, what happens when you try to create a rule or filter packets? BP Filter is going to create what's called a codegen, which is a structure which represents a client and a hook. So if you use IP tables trying to filter packets on input hook, you're going to have a codegen for IP tables and that hook. If you try to filter on the forward hook, you're going to have a second codegen for IP tables and that new hook, a different hook. It's completely transparent to the user, but internally that's how it works. And that codegen is used to generate the BPF programs. So it's basically a buffer of memory in which we'll write the BPF instruction one after the other. Another concept is the fix-ups. So let's say you want to count the number of packets, for example. And for that, BP filter has a function, BPF function, not a helper or a kfunc. It's a function inside the bytecode itself that's generated by the program, by BP filter. But when you want to call the function, you don't know yet where the function will be located in the bytecode. So what happened here is that it creates a fix-up, which is some kind of bookmark, which will be used later to fix the jump offset to call the function that will be defined later in the bytecode. Other thing we have is the custom function as I've described, which in BPF is basically you've got your main program, and then after that you've got another piece of code with an exit instruction at some point, and you can jump to that first instruction after the main program and run the function. So BP filter for now supports XDP, TC, and BPF net filter hooks. So XDP is used for NF tables. BPF net filter is used for IP tables. And TC is not much used anymore, but it could be definitely used. It's working, and it works fine. It's just that for now, IP tables is used with net filter hooks. All the programs generated by BP filter will use the dynamic pointers, the BPF dynamic pointers. So whether it's TC, XDP, or net filter, the generated program will first allocate a dynamic pointer and create the slice for the various headers if the headers are available, depending XDP or TC, for example. And finally, the counters. So each program will have its own map. And for each rule, if a given rule match the packet coming, it's going to update the counter for that rule. And in user space, you can see the content of the map and see which rule has matched how many packets and how many bytes. And because you will have one program per interface, you will also have counter per interface. So you know for, we don't have it anymore, sorry. But if you create a rule to drop every packet, you will have a BPF program for every interface dropping all the packets. And then it means you'll be able to know how many packets on each interface has been dropped because the counters are defined per interface and per program. I don't know if you can see that right, but that's roughly what bytecode generation looks like. So the emit macro is used to tell, basically add this instruction to the program. And one instruction after the other will add basically the rules inside the BPF program, inside the buffer. This is, for example, the call to the counter update function. So the function to update the counter is located after the program, and this is how it's called. So we set the right values into the proper registers, and then we call the function, and the function uses the values in the registers to update the map counter for a specific rule. And we can also see the emit fix-up call, which is basically what I was talking about, which is we can update that jump to the function later when we know actually where is the function located. The output on the right is what's received, what's coming from BPF tool output. So when the program is loaded and attached, you can dump the content, and that's basically what it looks like. Something's missing here, which is BTF info, as you can see. So it looks a bit weird when I call my function, because it has no name and no BTF info, at least for now. And from the command line, that's what it is. So you call IP tables with your --BPF flag, and it's going to use BP filter in the backend without you knowing about it. And then you can see that your program is effectively running on the system. There are two programs here, which are, the main difference here is that the O2, the first one is on the input hook, and the second one is on the output hook. But both have been created with BP filter, and will basically drop every UDP packet on the given interface here. And the programs are pinned in the BPF file system, so you can restart BPF filter and it's not going to change anything. You won't like let every packet pass on the system. It's completely fine. And so some performance number. So I take this with a grain of salt. So it's BP filter compared to IP tables. So at this point, the packet processing is done at the same point in the kernel, which is input in that case. So the IP table rules are located at the same point where the BPF program is running. If we were to use XDP, for example, it would be widely different. But it's, to me, I think it makes more sense to see roughly what it means if you filter at the same time. And the more rules you add, the faster it gets, and the more the gap between BP filter and IP tables grows. I've been working on benchmarks and tests for NF tables, but for now, for NF tables, it's quite new. So I'm able to create chains and drop packets and stuff, set policy on chains, and I'm almost done on IP filtering, IP address filtering. The trick here is that, again, I have to make sense of the net filter bytecode coming in the packet, coming in the request, and from the net filter bytecode, try to create the BPF code that goes with it. So it's almost done, but not done enough to make benchmarks. So it's not there yet, but soon. I've got a few links here, which are so the BP filter repository, but also the IP tables proof of concept with the --BPF flag, and same for NF table. And that's about it. If you have any question.
Hi, Quentin. How do you configure the daemon? Like, I take it the interface, you don't need to configure it in the daemon. The interface to which you want to attach the program, you get it from the IP tables rule. But if you want to change the XDP mode, for example, use driver generic or offload, do you support that at this time?
So for IP tables, it's not XDP, so it doesn't matter really. For NF tables, for now you don't. It's just the XDP generic mode. But it's still, so that's something that needs to be able to be configured, for sure. The NF table part is very early, and I'm working with Florian to get it integrated properly and have the right features. But eventually, yeah, the point will be to be able, so NF table is a way to use BP filter. It's not the front end for BP filter, it's a way to use it. So eventually, depending what Florian thinks, we might say that for NF tables, we always use the XDP generic, for example, which doesn't mean that I can't have like a generic front end, which allows me to do whatever I want, use any hook I want, and use any mode of attaching XDP program I want, if that makes sense.
Yeah, thank you. Another question. Do you have a way, or do you plan to have a way to query the daemon to retrieve the bytecode that you produce? Like, instead of trying to load and attach directly the program, do I have a way to just translate my rule and get the program back and do whatever I want, like deploy it on a variety of interfaces or hosts or whatever?
It can be done right now, but it's an interesting feature. It can be done because the way I work on it and I develop it, I need to attach it all the time. But yeah, ideally, BP filter wouldn't have to manage the program itself. So it could be focused on just creating the program, and then you do what you want with it. But there's no like generic user space tool to manage programs. And there is also the XDP issue where you can attach one program, and so. But ideally, yeah, I'd like to just create the program and don't worry about it. You do what you want.
Yeah, okay, thank you.
So I'm going to ask the dumb question.
So, this thing is technically called eBPF. So, what about having something like the BSDPF tools work to do the packet filtering using eBPF on Linux? Because, those BSD people, they keep talking about how they've got the better, packet filtering interface and all that other stuff. So if you're already making this to be work like a firewall and a packet filter, what about bringing the tools over too?
Sorry, can you repeat the question? Sorry,
I
Neil.
think I just stunned you into confusion. Basically, the name BPF, right, refers to Berkeley Packet Filter. And the part of it that we have in Linux is essentially the engine part, but we never had the tools part of it that the BSDs have. And a lot of people talk about how the BSDPF is better than ours or whatever. I don't really care about that part. What I care about is kind of for the lulz, can we have that tooling now work to do firewall things with BPF?
Well, yeah, I hope so.
All right. Yeah.
I don't know if it's satisfying enough for you, but
I had to ask.
I have a question about maybe the benchmarks. So I'm guessing that this is coming from the perspective of like a linear list of rules, and it's evaluating like performance of like the last rule that you hit or something like that.
Yeah. Sorry.
So maybe that's some context, and I understand that NF tables has come up with new different syntax to try to allow firewall rule writers to express more complicated things. So use maps, for instance. So similar, like drawing on IP set and various things like that. So I guess my questions kind of getting maybe to the expressibility of NF tables and the avoiding linear iteration to implement your firewall.
Yeah,
and
definitely.
how does that kind of
Yeah,
fit in
yeah.
with this?
That's why I was saying like take this with a grain of salt, because it's not exactly how you would define rules in real life. And for NF tables, you would, for example, create a set, and that's why I'm not publishing for now at least NF table numbers, because you can like just put a bunch of rules and throw packets at it, and obviously XDP will be faster than NF tables because it's before then and you don't have to allocate anything. But I'd like to work with Florian to actually have real benchmark that they run on NF tables and compare it to what it looks like for BPF filter, and have something that's really meaningful and that we can say, yeah, but you're doing it this way and we don't do it this way. So the benchmarks need some work, but I just wanted to have like a first overview of what it could be like.
Couple of questions here. Hello, can you hear me? For each rule, do you generate the separate BPF program?
No, so there is one BPF program for each interface for each hook. If you want to try to filter 5 different IPs for one for the input hook, for example, and you create 5 different rules, then you'll have one program with the rules inside, and it's going to be enrolled, and it's going to process the rule one after the other, but it's just one program.
I see. And then do you provide any dynamic rule injection mechanism? Like if I want to add the 6th IP to filter out, how one can do it? It's like replace the whole program?
So the old program, yes, needs to be replaced, because whatever happened, like the program is in the kernel, you cannot modify it. You need to reload a new one anyway. But something I would like to work on as soon as possible is try to regenerate just parts of the program and not all of it all the time.
Yeah, like dynamic rule injection could.
Exactly.
Yeah.
Have you tried playing on with how many rules to see how many rules you can support before the verifier gets unhappy?
The issue, I haven't tried to. So what I've tried is like making as many rules as possible. And the issue I had was that if the rule match, I would jump to the end of the program. But that at some point was limited because the jump offset is 16 bits. So I had to find a new way to actually get out of the program if the rule matches. And since then, I haven't tried, because one of the issues is, as we were saying, like I generate the whole program every time. And I should instead generate the rules, store it on the side, And when a new rule happens, I will just stick everything together to have the program and load it. Because for now, it's a bit slow. I've been up to like 6,000 rules, but not much more. But we could do definitely much more. There is space for it. I just need to be a bit smarter when I create the program.
Interesting, cool. Yeah, we do something similar. Do you generate everything in bytecode, or do you have like some functions that you make in C and compile with Clang, like some static functions that you have, like help?
Just bytecode. Just bytecode, and I use kfunc and BPF helper, obviously.
Frequent. What about chains in IP tables? Do you support them?
User-defined chains?
Yeah.
Not yet.
Okay. And what about external modules? So IP tables can be extended by out of 3 modules. I believe it's also not supported. And
no, for now it's basically IP source destination with a mask. Same for the port protocol interface. So it's basic filtering. I know that Mitri in his patch series has been working on UDP matchers, which are not supported here. And for now, discussing with the NetFilter maintainers, because that's also the point for BPF Filter to be used somewhere, is that I should more focus on NF tables than IP tables legacy, which is not much used anymore.
Okay, yeah, thanks.
I mean, maybe what you could probably do is like allowing users to have like their own custom C snippets and then inject this into specific points for the BP filter stuff, right? So that you have more customization if you want to.
Definitely. So BP Filter would focus on what it can do already. And if you have some quirks you want to do, you can inject C inside it. That would be great.
Thank you. Silly question. As far as I remember, there were some parts of the first version of BP Filter that were merged into the kernel, like the UMH part at the time. Given that you're moving everything or most of it to user space, what happens to the components that are already in place?
I was expecting Daniel to ask this question. I need to remove it, and it's going to be done. I commit to do it this year.
You're being recorded.
Yeah, I know that, and I will do it. Because it's not used in user space, in the kernel, sorry. The kernel module is not used, and it doesn't do anything, basically. There's no filtering into it. It's just like plug somewhere in the kernel, and that's it. And recently, someone found out that in Ubuntu, it's enabled by default. So in DMS, you can find BP filter message, even if it doesn't do anything. So I need to remove it, for sure.
Okay, sounds good.
I think the award for most questions for a talk goes to Quentin, definitely.
Yeah, thanks a lot. So somehow builds upon the question over there. So I think with BPF, you have a lot more expressivity in the language itself than you have with IP table roots and everything. So I think there is a lot of potential for optimization. So like putting several rules together in a clever way to optimize latency and so on. Did you think about that?
That's tricky. If you define your rules in a specific order, the program like BP Filter or even like IP tables or NF table or anything can't know if you're right or wrong. And that's something I've been discussing with NetFilter people, is that we need to find a way for the user to do better rules instead of optimizing stuff on the kernel and like user space side, whatever. There is actually a tool, I don't remember the name, but from an F table that will check your rule set and try to compact stuff and to create a set or something. And that's interesting. But yeah, it can't know if the rules are in the right order, and it can't reorganize and like say, okay, I've got like filtering an IP, then a port, then an IP. I'll compact the IP together and create a map of it and look into it, because the order matters.
Yeah, I mean, I'm thinking very easy, but maybe there's already things in the stuff about, but like you have hundreds of rules, filter this IP, filter this IP, filter this IP, filter this IP, that you can then, I don't know, have some masks on the things that you can express in BPF, in C code, basically, or in bytecode that you couldn't really do in the filter rules. But maybe this is already possible in the filter rules already.
I think maybe like one thing that is interesting, I mean, like if you look at the typical Kubernetes case, if you have many services that get installed, right? And then maybe you can have like some profile guided thing that looks at, okay, like it's most likely that this specific service is hit, but it's at the very end of the rule list. So maybe you could reorder it, at least things like that.
Yeah.
But it's tricky, I agree.
It's tricky, I agree. And like the whole optimization first of the bytecode generated and of the rule sets is a very interesting topic. Unfortunately, I don't think I'm there yet, but I'm more than eager to have a look at it, and I'd like to be at that point for sure, and try to make things faster too.
Here's just add one thing that's also tricky with combining rules is then you have to worry about what it looks like from metrics and counters. And if people have created a certain number of rules, then they usually expect to have all those counters or that they line up in a way. At least that's something we have a problem with.
I have a question as well. So you mentioned IP tables and NF tables. Do you also have like a programmable API where someone can link against the BP filter as a library and create the programs?
So now if you use libBP filter, you can send, there's a raw interface to send data, but there is nothing on the BP filter side to receive it. But I'd like to do something like that, because if you use IP tables, you're limited to what IP tables allow you to do, and same for NF table. And what if you want to create a rule and attach it to TC, for example? So I'd like to create a generic interface to be able to do that and have the full extent of features offered by BP filter.
All right, thank you.
Thanks a lot.
Getting that thing to blink is the hardest part about this presentation. Okay.
Click share again. Entire screen. You need to select. Share.
Okay, so now for something completely different. Normally, I talk about layer 1 issues. This time, I'm going to talk about a completely different subsystem. What am I talking about? Blinking lights. As you can see, RJ45 connectors. They often have a little LED in them that blinks. And it tells you if your networking's working or the cable's falling out the back or whatever else. There's generally two different ways they're controlled. Either the PHY or it's the MAC. Or in this weird diagram here, both. But nobody ever does that. And they're all different. There's no standardization. You look at 802.3, it doesn't say a word about LEDs or PHYs, these controllers. What they can do, what they can't do, which means that every vendor does something different. No standardization whatsoever. When you look at the control bits, they all look different. Makes it a right mess. It also means that the old vendors try to do something different because this is where they can differentiate. They can make their lights blink different to everybody else. Long, long time ago, 2010, Marvel put in their first way of doing it in the device tree. Basically, select page 3 in the PHY, register 10, mask it with 0, and write 242 hex to it. Which, if you've got the data sheet, you can figure out what that means. I can't. I don't have the data sheet. Nowadays, the D team internal would run away screaming and say, no, you're not allowed to do that anymore. You're not allowed to write random values into random registers anywhere. But this was 2010, and we didn't have to do anything better. Got slightly better 2018. At least then it had a name, and it was just for LEDs. But it's still a collection of values which you wrote into a register. Or at least it was only the LED register and not anything else. What's wrong with this? There's no consistency. You kind of expect the LED to say the same thing all the time, or you expect some sort of consistency. It blinks, that means the packet's probably come and gone. It's lit, the link shows us a light, shows you got link. So even though there's no standardized consistency, user experience should be consistent. There shouldn't be any reason why every vendor needs to do it differently. Yeah, they do. It's also not really a thing that should be in device tree. Device tree is supposed to describe the hardware, not the configuration of the hardware. And the other thing is that we as users want to configure this, not necessarily the person who writes the device tree. So there's lots of discussions and lots of vendors still trying to do their weird way. And there's lots of discussions about this, and eventually Florian came up with this. He kind of summarized it, what we thought. We should all try and do it the same way. We should define the subset of standard meanings. And this was the first time that somebody actually mentioned, why don't you use the LED subsystem of Linux? Because Linux knows how to blink LEDs already. Seemed really logical at the time. But the usual problem, nobody had any time to actually implement it. So people coming along with all their hacks, and we said knack, and we said knack, and we said knack again, and we keep knacking them. If those people had actually got together and spent their time implementing what they said, we'd have got something in much faster. But no, we keep sending knacks, and they keep trying. So this is one of those lesson learned sort of things. Before you try and submit something, please search. Has it already been knacked? It's likely to get knacked yet again. And that comes up all over the stuff that I look at in the networking side. People repeatedly post the same thing and expect it not to get knacked. So, learn your history, otherwise you'll repeat it. The other thing is, there's a tendency to solve it for my driver and not solve it for everybody. That's again something I tend to point out to people who are submitting code. This isn't a solution for your driver. This should be a solution for everybody. There's too much silo thinking at times. I work for vendor X. I only work on driver X. Everybody else is somebody else's problem. And it shouldn't be like that. It's got a bit better. People are doing reviews outside of their own silo now. But it's still not so good. And you can learn a lot from looking at other drivers. The page pool is a good example of this. I'll solve it for everybody, not just for me. There's a few drivers that have got something like the page pool already. But then somebody came along and said, oh, well, let's make this generic, and everybody can use it. That should be the default thinking. Please solve it generically. It's probably not specific to your hardware. And there's other things that people always get wrong. Sometimes I review lots and lots of code. Everybody gets pause wrong. Everybody gets energy efficient Ethernet wrong. Why? The API is bad to start with. It's poorly documented. And if you're finding in somebody else's code to copy, it's probably wrong there as well. The other thing that's going wrong here is that suppose you end up setting 2 bits on your hardware. But to get to those 2 bits, you've got to do quite a lot of understanding of the API. Why isn't that in the core? And then the core just says, set this bit here or set that bit there. And now with FileLink, we've done that. So FileLink drivers tend to get this right just magically because FileLink does all the real work and they just do set their 2 bits. Energy efficient Ethernet, there's a set of patches around about which will throw away 80% of the code in the drivers, centralize it. Hopefully most of these bugs will go away. So make the core do the work, not the drivers. Keep the drivers simple, which is not always simple because these drivers are huge at times and they do all sorts of silly things, but try and get as much of this stuff into the core as you can. This is where I see how many grey beards we've got. Who remembers Rusty Russell? 2, 3. This goes back a long, long way. 2008, I think. He came up with a metric about how good APIs are. Then you can't get it wrong. Through to 1, if you read the right mailing list, you might get it right. And there's various levels in between. Fortunately, our pause API probably fits to 1, and just nobody actually reads the mailing list. If you really want to cause people trouble, there's actually also -1 through to -10, and there you're trying to design APIs which nobody can use. It's a deliberate design decision to make them bad. It's worth reading. Read the whole set from Rusty Russell. Hopefully then you'll produce better APIs, and you won't mess up my life of trying to review this stuff. So, how do we get this right? I can't take too much credit for this. Christian Marangi did most of the work. I just pointed in the right direction every so often, did the review work, and I actually did the Marvel Phi. He did the Qualcomm stuff and the core. In networking, we've kind of got this rule for offloading. We start with what Linux can already do, and then we try and give it to the hardware to do. What can Linux already do with LEDs? You go and look on your machine, or a machine, say this class LEDs, you'll find a list of all the LEDs that's on the machine. And this is from my laptop. So things like the numlock key, the shift key, this little red button light, they're all controllable. I can turn them on and off and everything else. So within that directory, there's a brightness file. There's a few selections of files. I'll just quickly explain how you use them. Brightness, put 0 there, and it goes out. Pretty logical. Put a 1, it lights up. The backlight for the keyboard on this display has 2 different levels. So the max brightness value is 2. So you could also put 2 into that brightness thing, and it will glow really bright. So you put 1, and it dimly glows. That's for user space, but we're more talking about kernel space. The kernel can control these LEDs itself, and there's various triggers to do that. You allow it to say, oh, I've just done a write to the disk, make it go blink. There's a trigger for that. You want to show that you've turned the radio off for RF kill. There's a trigger for that. You can get the very subsystems to control the LED. And just a very simple example, heartbeat. You can't arc beat to the trigger, the thing will start blinking like a heart. And it monitors the CPU load. And as the CPU load goes up, it blinks faster. So if you ever want to know has your kernel crashed, set that up on your shift lock key or whatever else. And if it stops blinking, your machine's dead. Okay, so back to networking. There was a netdev trigger already. Didn't do everything we wanted, but it did most of it. So you select the netdev trigger, and suddenly you get a few more files in there. Things like half duplex, link 100, TX, RX. If you give it the name of the interface, and you say 1 to RX and 1 to TX, you then start blinking on packet activity. And you can do that on any LED. So your numlock can show you the network activity if you wanted. You could make your backlight of your display show you network activity. It's an LED. This works for any LED. But ideally, you want it on your RJ45. Don't have to do, but you could do. So we needed to extend the API so that we can get the hardware to blink for us, not software. And this is extending with this class LEDs a little bit. First one's the standard interface. Set the brightness. If you've got that, you can do everything in software. If you want to actually offload it, then you need a few more. You need to implement a few more ops. First one is, can I even offload this collection of things that the user wants to see? So you could say, can I offload RX and TX at the same time? And it will say, sorry, no, yop, not stop. Can't do that. Because some PHYs weirdly can't show RX and TX at the same time on some LEDs. They're all different. It's a vendor differentiation. They screw it up in their own way. So once you've asked it, can it do this? And it says, yes, I can do this. Then you can actually ask it to do it. And that's what the next one does. And there's a reason there's two separate things there because it's quite expensive to swap from one to the next, and you don't really want to do it unless you know you're going to succeed. And then the last one is about what device am I actually blinking for? You don't want to try and offload blinking of network activity to ETH1 when it's actually being driven by ETH0. You've got to stay with software for that setup. So you need to know, what am I connected to? What's my upstream device? And that's what the last call's for. If all this fails, you go back to just blinking in software, which is how we do things in networking. If you can't offload something to the bridge, a hardware bridge, you leave it in software and let it do it in software. Maybe less so if you're working at 100 gigabits per second, but if you're talking about little switches that I tend to work with, yeah, we just leave it in software. The bit that probably gives us a Rusty Russell score of 7 or 8 is this flags thing, and it's a bit not so nice. You've got to somehow describe what you want it to do. And you end up with a bitmap. If you want it to show link, you set bit 0. If you want it to show it's got negotiated 10 megabit per second link, you set bit 1, and so on and so on. Often, in the little example here, you'll say, show me link on the left LED, show me activity, which is a combination of RX and TX on the right one. You're done. Questions? Because it's as simple as that.
Okay, I'll start. So you gave us examples of APIs which people always get wrong. Can you think of something that people is like not trivial, but usually driver routers get right?
Sending packets, mostly. Receiving packets. Actually, that's the bit I generally don't look at because that's something they always test.
Yeah.
They generally normally get the name of the driver in the ETH information. They get all the, the trivial stuff.
Right. I think we document things like in 3 different ways, right? One way is to write documentation under documentation/whatever. The other one is to put kdocs in the API.
Yeah.
And the third one is to have an implementation that you can point people at. And I wonder which one of those, do we have to do all 3 because then we have to keep them in sync, right? Like, is one of them more important?
think having a good reference is useful. It's the other problem is getting people to realize there's a good reference and go and look at it. They just tend to look at some other driver and copy it. And often you pick the wrong driver to copy, and you just copy all the bugs from that driver. So I tend to recommend for simple drivers, go look at the FAQ. And for big drivers, I don't recommend anything because I don't review them.
Other questions? All right, thank you. And that concludes, I think, the BPF on networking track. Thanks to all the speakers, and also big round of applause for Daniel, who organized most of the track and put everything together. Thank you.
Maybe one thing to note, so in the evening, there's the evening event. So please go and join that from the LPC. Yeah. And see you all next time.
None of those.
It's over.
Chair.
So even now that it's over, you still gotta wait till 6.
Yeah, contract.
Yeah, that's literally what I want.